I think maybe we just wait 1 minute. Actually, now it's 9:01. Do you think we should start, or should we wait until 9:02? I think we wait 1 more minute. People are coming in right now.
Okay.
And we are allowed to have a more relaxed ambient here on a Friday.
Well, those Spanish rules.
Catalan.
Excuse me. Yeah, I think Andre is not here yet. We should wait for him.
Oh, that I wouldn't count on. On the other hand, yes, okay, maybe for this talk.
Yep.
So when it hits 9:02, I will kick us off. So, welcome to the last evening or morning or day of the workshop. So our first speaker this morning is Marcello Fiore, who will talk about stable species of structures. Please go ahead, Marcello, whenever you feel like it.
Okay, so thank you very much, Joaquin. I want to thank you and David for organizing this very nice workshop and invited me to speak at it. What I want to do today is talk about the very recent work, which is joined with Segal Galal and Hugo Paquet. And it's about introducing a new kind of species, which we have called stable species. So the main thing of the talk is really trying to convey the ideas of how one actually reached to this new kind of structures. So to do that, I will go through some background, explaining where we are coming from. And this really is happening from two lines of developments that actually started in the 80s. One is from logic and computation, and started with the work of Girard that in fact led to linear logic. And the other one is from combinatorics and category theory, started with the work of André Joyal on species of structure. So these are two kinds of structure that we have actually seen during the workshop. The ones that were introduced by Girard, they can be thought of as power series, I mean set value power series. So one such, say from the discrete category or set of natural numbers to set, is to be understood as a family of coefficients or variety that will generate an endofunctor. And we have seen this many times during the week, that what we are generating are endofunctors that are of the polynomial type. On the other hand, the species of structures introduced by André, they are a bit more subtle because they come equipped with a symmetric group actions. And this symmetric group action is important because it explains how the structures are changing depending on renamings on their labels, and generate some more sophisticated kind of power series, which are of the exponential type. They are the coefficients of the species quotient by the symmetric group actions. Okay, in these two works, both Girard and André characterize these kind of functors. In one line, we obtain what I will call here the stable ones, which we have seen during various talks. They are finitary and Y pullback preserving. I'm using this terminology of being stable because it's the one used in the computer science literature, because this notion of pullback preservation arose in computer science from the study of sequentiality. And these functions were named by Gerard Berry as the stable ones. On the other hand, the functors, endofunctors on set that are induced by species of structures, they have a slightly weaker preservation property. They are finitary, but they preserve Y quasi-pullbacks. A quasi-pullback is a commuting square such that if we take the pullback of this cospan and look at the unique induced map, we get an epimorphism. Okay, this was the beginning of the subject, and then it was taken further. So in the set theoretic world, Girard noticed, and this is what led to linear logic, that the stable functions between index sets corresponding actually to linear ones, in the sense that these are set value matrices from some set which is to be thought of as the monomials on X to Y. However, well, Girard managed to construct a model of the lambda calculus in this setting without actually describing a Cartesian closed category. And that problem was considered by Paul Taylor. He needed to do this to move to a group theoretic setting and introduce so-called grids, about which I will hope to talk a bit later. These are groupoids equipped with some extra structure. And in that setting, he constructed a model of intuitionistic logic, namely a Cartesian closed category of stable functors between certain domains induced by these grids, and equip them with this linear decomposition as you see in linear logic. On the side of combinatorics, with Nicola Gambino, Martin Hyland, and Glyn Winskill, we introduce generalized species of structures. These again are linear functors, namely profunctors, from a free symmetric monoidal completion of a category, which again, one has to be thought of as, in this case, commuting monomials into another category B. And we show that this category was Cartesian closed. It's one of the examples that Andre was mentioning in his talk. And they are in one-to-one correspondent with the generating exponential functors, which generalize the generating functors on species that I mentioned before. Here and henceforth, I will write P of A for the pre-sheaf construction on A, which will appear throughout the talk. The question arises as to whether these generating exponential functors are actually analytic. And in fact, I don't know the answer for arbitrary categories A and B, but I have shown that when A and B are groupoids, this is the case. So the generalized species on groupoids are in one-to-one correspondent with the analytic functors as I introduced them before. Okay. So groupoids also are the main kind of examples that appear in combinatorics. They also appear in the work of Paul Taylor. And so our work here will also be based on it. And the direction in which we are ordered is to get in these two research directions closer. By that, I mean that we're going to construct a model of classical linear logic of a refinement of species of structures, namely stable ones, by which we actually mean a mutation of generalized species in the direction of being linear that will correspond to stable functors. And in categorical terms, this model will be constructing is essentially building a star autonomous category with something called a linear exponential comonad that I will explain later on. The important thing of this structure is that it induces a Cook-Leslie category that is Cartesian closed. And this will be our Cartesian close of stable species of structures. Okay, so my plan now is to introduce the ideas little by little, explaining how you arrive at this model. So we need to kind of bridge the gap between linear species. In this case, I'm looking at the monosorted one. So this is the category of index, natural number index sets, and the species. This is the pre-sheaf of a set to the category of finite sets and bijections, or if you wish, finite cardinals and bijections. So there is a forgetful functor and a left adjoint that makes every linear species into a species by acting freely. Okay. Now, one way to understand this linear species within the whole world of species is by looking at their actions on elements. So here I have a structure C sigma acting on tau, and if tau actually fixes the structure, then it's the identity. So in fact, what we need to concentrate on is on what is called the stabilizers of a structure. These are all the maps that fix the structure. And in this case, we see that we get the identity. This is in fact a characterization of linear species. So a species is linear whenever for all of its structures, the set of stabilizers of it, and that is all the permutations that fix the structure under the group action, is nothing but identity. So looking at the linear species and the interaction, let's say, between linear species and species in this way was an idea by Paul Taylor. And more important is that he proposed to consider degrees of stabilization. So I will explain what I mean by that as we go along. Okay, so to do that, we need to have a look at these stabilizers. So here are some well-known facts that will lead us to the axiomatization that we care about. So first of all, the stabilizers of a structure S, again, all the permutations that fix the structure form a subgroup of the symmetric group. These stabilizer subgroups are closed under conjugation. So what we need to look at is that for every finite set, say, of n elements, all the collection or the family of all the subgroups arising from stabilizers. Okay. And this is what we are now going to axiomatize. We axiomatize it by defining the notion of a kit. So a kit on a groupoid is an assignment that to every object of the groupoid associates a family of subgroups of the group of automorphisms on it. And these have to behave like stabilizers in the sense that they have to be closed under conjugation. Okay, so this is a kind of an axiomatization of the stabilizers of a species. And we are going from now on work with these kits and build a model on top of them. I would say the combinatorial character of this kit is clear. There are somehow specifications for the stabilizers that you are happy to admit. Okay. And as such, what they do is determine a subcategory of presheaves of the presheaf category, which we call the stabilized presheaf. So the stabilized presheaves are all those presheaves such that when we look at all the stabilizers of every single structure in this presheaf, belongs to the specification of the kit we are looking at. Okay. So all the presheaf P such that the stabilizer of every little P, say a structure in P of A, belongs to the, well, it's a subgroup in the kit A. Okay. Now here are some examples. So first, notice that the terminal presheaf is a stabilized presheaf if and only if the whole group of automorphisms of every element is in the specification kit A. Okay. So typically, when these kits don't have the full group of automorphisms of an object, the terminal object is directly ruled out from being a stabilized presheaf. So in most examples, these stabilized presheaf categories do not have a terminal object. Now going back to species, what we see is that there are two extremes. We can stabilize by taking all possible subgroups, which means that we impose no restrictions on the presheaf, and therefore we get the full presheaf category set to the finite sets and bijections. Or actually we can stabilize by forcing the only stabilizer allowed to be the identity. And in that way, we recover actually the linear species. Now, it's important to note that this we regard as a full subcategory of the category of species. And so the maps between these linear species are those between the species. And that is that we are not looking at set to the natural numbers, but we're looking at the Claesley category for the free species on set to the natural numbers. So here we're talking about linear species, but with kind of species maps. And this is really crucial in aiming at the Cartesian closed category later on. Okay, so first, this category of stabilized presheaf are not very wild in some sense, though they might not be so easy to understand. They are generated by taking the representables, quotient by them by all the groups that are allowed by your kit, and then closing that by arbitrary coproducts. Okay. Now, these kits have a clear combinatorial character, and what I want to do now is to equip them or restrict to those that have also a logical character. And what I'm going to motivate this by constructing a Boolean algebra associated to a group. I have not seen this construction elsewhere, and I will be grateful if people can connect it with something else or give me any feedback on it. So how can we do that? So take a group A, think of it as the group of automorphisms of one object in a groupoid. And we want to give it some logical character. So we consider the poset, actually the algebraic lattice of all subgroups. And if we do a Yoneda embedding into the two-element Boolean algebra, we obtain the free frame. This is a Hating algebra, or even a complete Hating algebra, and it's a good, well, it's a first candidate for families that could have logical character. Okay? These are going to be families, elements in here are families of subgroups that are downward closed. However, it's not good enough for what we want to do. And much better would be to actually take something like would be called the canonical frame, which is forcing all the distributive joins that are available in the post set of subgroups to be, well, we cut down the free frame while still preserving all the distributive joins in the post set of subgroups. Okay? This is like imposing the canonical topology in some sense. But what we need to do here is really to look at the Boolean algebras rather than Hating algebras. And so what we want to do here is to Booleanize this canonical frame. So we take the double negation close elements in there. And this I call the Boolean algebra associated to the group. So if we think that this group is the group that arises from the group of automorphisms of elements of objects in a groupoid, every such element comes with a Boolean algebra associated to it. And we're going to do that, we're going to use that in a second. Now, working with such a Boolean algebra in this abstract level is not ideal, and so I'm going to give you a characterization. Before that, let me just point out, there are many possible logical kind of kits that one can look at or frames. So there is the free frame. This is not very interesting. One could take a Scott frame. This would consist of the families that are downward closed, but also directed closed. Paul Taylor's creed are out in this way, and they would be, they can be described in this framework. They would be consist of the directed families that are in fact extensional. And by this, I mean that the whole, the families of groups is completely determined by the union of the subgroups in the family. Okay. So one of these families of groups is extensional whenever it consists of all the subgroups of the group we are looking at that are included in the union of the family. But the canonical frame actually is stronger, and one can give a reasonably explicit description, but I'm not going into that here. All this, so I would say that to pursue this work in the direction of intuitionistic logic, one should concentrate on this canonical frame. And this we are going to do at a later stage. But what we want to do today is concentrate on the classical viewpoint, and so look at this Boolean algebra. And now I'm going to characterize it as by a classical technique that is used in linear algebra of double orthogonality. So to this end, given a subgroup of a group A and a subgroup of the opposite, we say that these two subgroups are orthogonal precisely when their intersection is trivial. This is very much like the notion of orthogonality that arises between vectors in a vector space. And once you have that, you can consider orthogonal complements. So a family of subgroups induces an orthogonal complement consisting of all the subgroups that are orthogonal to every single element in the family. This is again like you do in linear algebra. And now it is a theorem that the Boolean algebra we are constructed is in fact consists of all the families of subgroups of the group that are double orthogonally closed. Okay. And in fact, all our work really relies on this, and all the calculations that we need to do are using this characterization. Okay, so here are some simple facts about orthogonality. So X implies not X. So I'm going to try to start reading this in logical form, because one of the aims I have here is to show you that this structure have both logical and combinatorial character. And I spent some time with the combinatorics. Now I'm moving to the logic. Then I will go back to the combinatorics. So if X implies Y, then not Y implies X. The orthogonal of the empty family is the full family of all subgroups, and that is the truth values true. While the orthogonal of true is the trivial, the family that only contains the trivial subgroup, and that is the truth value false. Conjunction in this Boolean algebra is intersection, while this junction, and this is something typical that we see again later on, is obtained by taking the union of families. This need not be double orthogonally close, and so we have to do that. Yes, I should have an extra orthogonal here. Sorry about that. Okay, so now we come to the first main definition of the kind of structure we want to look at. This we call Boolean kits. So there are kits out before, so families of subgroups close under conjugation. But now we want them to come from the Boolean algebra associated to every object of the groupoid, and so they have to be double orthogonally close. So one way to think about this is that a kit provides for every object of the groupoid a truth value in the Boolean algebra associated to the group of automorphisms of the object. So one could think of examples of groupoids coming from fundamental groups of spaces. And in that case, what one is doing is these Boolean kits are associating to every element of the space a truth value that lives in the Boolean algebra, well, in the intrinsic Boolean algebra associated by the symmetries of the that are in each in the group of each element. Okay, so now the first remark here is that if A is a Boolean kit and now I pointwise take orthogonals, I obtain a new Boolean kit. This means that the orthogonality is close under conjugation. And that is very important because now we can amalgamate the dualities from groupoids, namely by taking opposites, with the duality of Boolean algebras, namely taking negation. And so we have a star operation that given a kit, a Boolean kit, AA, gives me the opposite of the category of the groupoid and the negation of the kit. And so what we want to do now is actually look at the profunctorial structure between such Boolean kits. Before we do that, here are some properties of the Boolean kits. So they're downward close and directed, and so the representation that I gave before can be a bit sharpened. So they are generating actually by quotients of representables under finite groups in the kit. Then taking finite sums and then filtered colimits. Boolean kits are extensional, and so they are crits in the cells of Poyle-Taylor, which means again that they are completely determined by the family is completely determined by the union of all the subgroups in it. And so I'm going to introduce this notation for an element of the union of the family of subgroups in a kit, which I'm not sure how I want to read it, but sometimes I say alpha realizes A, or sometimes I say alpha supports A, or alpha asserts A, or alpha verifies A, but you get the idea. And in fact, this has a logical flavor to it, because now a family A is included in another one B, if and only if, whenever alpha supports A, then it supports B. Every alpha supports true. Alpha supports false if and only if is trivial. Here is an interesting fact. Alpha supports A if and only if all its powers do. Okay? And we will see this playing a role later on. And if alpha supports both A and not A, then actually supports false, that is trivial. This notation and some logical framework will also appear before when we discuss further structure. So what we want to do now is provide Boolean kits with a linear setting. And so we want to consider extending profunctors between groupoids to what I will call stabilized profunctors between Boolean kits. So to motivate the definition, we have the following desiderata, is that whatever definition we come up with is close under duality. So if P is a stabilized profunctor from A to B, its dual P star should be a stabilized profunctor from B dual to A dual. Another desiderata is that in fact we have Boolean fibers. So the whole Boolean algebra structure, say on a groupoid C, is going to be mimic in this category of stabilized profunctors, and is going to be kind of tracked by the identity from C to C. So A is included in B. These are two Boolean kits over C, if and only if actually the identity is a map from the C equipped with A and C equipped with B. Okay. So this motivates our definition of stabilized profunctor. Okay. So it's a profunctor from groupoid A to groupoid B such that the following holds. So suppose you have a structure P from B to A in the profunctor. So a relation in the profunctor P, by this, denoted by this squiggle arrow. And now you have alpha and beta that act on it, on the left and on the right. And in a sense, they are an action and a reaction. So if alpha acts on P, it gives me a new element that is counteracted by beta, in the sense that if beta acts on that element, I get P back, and vice versa. If beta acts on P, I get a new element that when I act it upon alpha, I get P back. So they are kind of an action-reaction pair, this alpha beta. Then it should be the case that if alpha asserts A, beta asserts B, and moreover, and dually, if beta asserts not B, alpha should assert not A. That's the definition of these stabilized profunctors. One shows that they are actually close under composition. So the desiderata 1 and 2 hold with this definition. And so let me give you some examples. So every profunctor from A to B is actually stabilized. From A equipped with a false truth value and B equipped with a true truth value. Okay. This is not very useful in a sense because even though profunctors will, every profunctor is stabilized, you can see that you cannot necessarily compose them. More interesting, and now we see that the stabilized profunction capture the ideas we were after, is that the stabilized profunction from A with the truth value true to B with the truth value true are nothing but profunctors that are free on A. And now we see that this notion is actually capturing being free, which is in turn capturing being stable or polynomial. Okay, so we obtain a bicategory of Boolean kits, stabilized profunctors, and natural transformation between them that projects to the bicategory of profunctors restricted to groupoids. Okay, and this is a result now that the byproduct and compact Hall structures of profunctors lift to a byproduct and star autonomous structure on stabilized profunctors. So I will show you how this works in a minute. So first, for the byproduct structure is given, well, on groupoids we know what to do because we are lifting the structure, so it's the sum of groupoids. And it's also the sum of the truth values. And we have that an injection of alpha satisfies the sum of i's if and only if alpha satisfies the indicated AK. Now, let me indicate how the symmetric monoidal structure works. The unit is the terminal category with the only possible kit you can put on, Boolean kit you can put on it. And the tensor product has to leave the one from profunctors. So you take the product of the two groupoids, and now you take the product of the truth values, which consist of all the families, the families of pairs, that have elements coming from one from A, from the Cartesian product of some group in A to another group with another groupoid in B. This set, this family is not double orthogonally closed, and so we make it a Boolean kit by taking the double orthogonal. So this is a double orthogonality is not, or Booleanization is not a trivial operation. One has to prove that the structural profunctors stabilized. And if we look at why this is the case for the associator, the crucial point in the proof is the following logical rule that is supported by kits. If a pair XY realizes X times Y orthogonal, but X asserts, little x asserts capital X, then necessarily Y asserts not Y. And this is something that you can prove, and it's the crucial fact for which the associator actually is an stabilized profunctor. Okay. We also have star autonomous structure. This star autonomous structure is proved by showing that the usual bijection between profunctors from A times B to C op and B to A times C op is preserves being an S profunctor. So a profunctor on top is stabilized if and only if so it's isomorphic one below. Okay. This is a technical proof actually. Okay, so now this induces a dual to the tensor product given by taking the dual of each of the Boolean kits and then dualizing further. And we see that what we obtain, unlike in the by category of profunctors, is not a compact closed category, because the kit associated to the dual of the tensor product is quite different from that associated to the tensor product. This dual of the tensor product is very important because it gives me closed structure. Okay. And this is the formula. And again, we see that is the usual formula for groupoids in profunctors with the associated truth value. Okay, so now I want to show a bit of the combinatorial flavor of the model. And so here is a combinatorial example. So consider the linear function space from bijections with true Boolean assignment and bijections, finite sets and bijections with true. The formula tells me that this is the groupoid of bijections of times bijection of with this truth value. Okay. And the question is when a permutation in bijection of and another one in bijections belong to it. And actually you can prove, and this is something that has combinatorial meaning. Sigma tau are in this truth value if and only if the order of one permutation divides the order of the other one. Somehow at this moment, this is something more of a strange fact rather than anything one can do something with. But it shows that there are close connections to combinatorics that eventually we would like to explore. Okay, so now we have a linear framework, this by category of stabilized profunctor, and we want to go towards one that supports the function spaces. And so for that, we need to consider exponential structure. Okay. So first, we look at it on profunctors. This is something we have done with Nicola Gambino, Martin Hyland, and Glyn Winskill, that you can actually take the symmetric monoidal completion, which, as I said at the very beginning, is kind of the categorical way to talk about commutative monomials, and lift it from cut to profunctors. This actually is what is called a linear exponential comonad. It's a terminal definition, but the crucial point of it, and which in fact it was already observed in the first paper by Andrea on species, is that the free symmetric monoidal category on a sum is equivalent to the product of their free symmetric monoidal categories. Okay, so what we want to do now is to lift this to stabilized profunctors. And what that means is that we need to define when some map in the symmetric monoidal completion should belong to a bank kit. Okay, this is our lifting for this construction. So I'm going to motivate a bit how one does that. And to do that, we need to look a bit at the symmetric monoidal completion. So it has objects given by sequences and maps given as in the FAM construction but restricted to permutations. So you clearly see that if A is the terminal category, all this data here vanishes and we are left with permutation, that is with the category of finite sets and bijections. And you compose them as in the FIME construction, but here I'm going to show it by looking at the cyclic decomposition of a permutation. So this is a map alpha from the sequence 0, 1, 2, A, B to itself. Map 0 to 1, 1 to 2, 2 to 0, by a maps alpha 0 from 0 to 1, alpha 1 from 1 to 2, and so on. Now remember that a map is in the kit if and only if all its powers are. So it makes sense to look at the powers of alpha. And what we see is that there are some endomorphism loops appearing there. So, and this depends on the length of the cycles that your permutation decomposes into. So in alpha square, we already see a loop on A, and in alpha cube, we see loops on 0, 1 to 0, 1, 2. Okay. And these loops are crucial in the definition of this bank kit. Okay. So here it is. The bank of a Boolean kit A with truth value A is the free symmetric, is the symmetric monoidal completion with kit given as follows. An automorphism is thrown into the kit if and only if all its loops are actually in the kit A. This family need not be a truth value, so we take its double orthogonal completion. Okay, and you see clearly that if we are taking the bank of some A with true, we get back true. And so in this case, we are essentially doing what was being done in this generalized species world. Okay, so now the theorem here is that S-prof with the tensor, well, with the tensor product, the duality and this new operation is by categorical model of differential classical linear logic. And the important thing for us is that it induces a co-Claisley by category that is Cartesian closed. And this is our Cartesian closed by category of stable species of structures. Okay. So here is an example. If we look at the stable species of structures from the unit of the tensor product to itself, we recover actually the linear species. Okay. And as I said, with the but with the map of species, that is the Claisley category of set to the natural numbers. Okay. Now we have a projection from stable species to species restricted to groupoids, and this projection preserves all the Cartesian closed and differential structures. So really, all the structure is as we know it from generalized species, but with taking care with these Boolean kits of how we deal with being free. Okay, so now that covered all the intentional part of the work, and so now I want to talk about the extensional part, which is the functors that these structures produce. So take a stable species from A to B. It happens to restrict then to a functor from the symmetric monoidal completion to stabilize pre-shifts. And this, by Kahn extension, induces an analytic functor between pre-shift categories. This analytic functor is nothing but the usual exponential power series formula. Okay? We take the sum over all the monomials of P at the monomial product X at each point of the monomial. And now it so happens that this restricts to stable to the stabilized pre-shift, and in doing so, the analyticity becomes actually stable. So this map is analytic. Analytic functors present the epimorphisms, so it's epipreserving. Analytic functors are finitary, so it's finitary. analytic functors, they preserve wide quasi-pullbacks, but when restricted to stabilized pre-sheaf, they actually preserve wide pullbacks. So they're local right adjoints. Okay, so now we have a bioequivalence between the intentional wells of a stable species and a two category of stable functors. This has as objects the Boolean kits, the stable functors between them, and crucially, the Cartesian natural transformations. And this is imposed upon you by the fact that you are after a Cartesian closed category. Without this Cartesian natural transformation, stable would not be bicategorically Cartesian closed. Okay, in fact, this bioequivalence restrict from stable species to stabilized profunctors. And there we have another bioequivalence between them and a two category that we call linear. So this has as object the Boolean kits, and as one cells, the functors that are linear between their categories of stabilized pre-sheaves. And in this context, to be linear means to be a local left and right adjoint. Again, restricted to Cartesian natural transformations between them. And the upshot of what we have done then is that we obtained a linear decomposition of the stable functors as linear ones on exponentials, Boolean kits. So, yes, I think this is all I want to say. Thank you very much.
Okay, thanks a lot, Marcello. So are there questions or comments?
I have a question.
Please.
Hi, Marcello. We know that the monads in the bicategory of generalized species are operads.
Yes, so here they are.
What are the monads in your bicategory of linear?
So we know, yes, we know that they are symmetric operads. Here they are non-symmetric operads.
Thank you.
Yeah, so one thing I want to do, so I have a friend, I have used the Cartesian closed bicategory structure of generalized species to recast in a purely algebraic way the Weiss-Dollans-like construction. So I should be able to reproduce it in this context to do that, not for symmetric operads, but for non-symmetric ones. And that is something that I believe is going to go through, but I have not checked.
Thank you.
Okay, I think it was Torsten next.
Yeah, I was just, I try to relate this to our perspective. So I have a question. When you I mean, I guess these functors are, I mean, it must be closed under composition, right? I mean, do you consider the composition of these functors, or?
I mean, the composition of these functors is straightforward from their.
Yes.
I mean, they are finitary epi-preserving local right adjoint. So.
It's just that when I looked at this, I found that I need axiom of choice to define composition.
Oh, here. Well, first of all, I don't know if you have anything against it, but we need to use a lot of classical logic.
Sure.
Okay,
yeah.
so that's one
You
point.
don't care, basically.
Sorry?
You don't care, basically.
Well, it's not that I don't care. I'm talking about Boolean logic. So.
Sure. No, but I mean, sorry. If you go one
and about the axiom of choice.
No, I mean, even the composition of these analytic functors, right? So I wondered whether it helps to restrict it, whether you get a better behavior. If you go one slide before, maybe?
Yes.
Yeah, this. So these functors in the pre-sheaf from PA to PB, right? The pre-sheaf, PB, and so on. If you want to compose them, I need axiom of choice.
No, you don't, because I mean, you can compose them, for instance, by restricting and taking can extensions. So really, you don't need. Okay.
Okay, but I want to have another analytic functor in the end. You see, I mean, I have two analytic functors or
Yes.
two quotient containers, and now I want to oh, okay, hang on. This, yeah.
Yeah, no, there is no need for any axiom of choice here. I mean, up to yes, we're working up to isomorphism. I don't think there is any need for that.
No, that's not the point. Okay, I guess it only okay. No, I think the situation is slightly different. It's when you have set to set, because otherwise you cannot compose them. So it's a different situation. Yeah. Sorry, I look in the composition in a different direction. So yeah. Sorry.
Yeah, I'm not sure I understand. But if I define them stable as having these properties, then I take the composition of two functors and they still have these properties. So
yeah. So the composition for me goes in a different direction. I consider endofunctors from set to set, so pre-sheaves over set, right? And you don't even look at this, so the question doesn't really make sense in your context. So sorry.
Okay.
Okay, next is Paul, please.
Hello, Marcello. I'm sorry to arrive a few minutes late, and I'm sorry that I can only give you a fraction of my brain for reasons that I told you. But anyway, a nice talk.
Thank you.
I have a feeling that only half a dozen people ever read my paper because it was quite difficult. And your structure seems to be a step up in its complexity. So one of the things that fell out of my structure was a kind of type of types.
Yes, so
you get one in your construction?
I have not looked into it, but I would think so.
Yes.
So I know you have dependent sums, dependent products, and type of type. I would expect this to be there.
Yeah.
I have not checked it, but I would think so.
Right. Okay. Right.
Yes.
Very good.
Yes. That's another thing that yes, we want to do.
What brought you back to considering material from 30 years ago?
Well, you know, my two co-authors are French, so that's one thing.
Okay.
But no, more seriously, I've been wanting to understand why all these models, the generalized species that we talk about, the ones that Andre talked about, which are based on symmetric monoidal categories or Cartesian categories, and so on, they're all Cartesian closed categories with on monads that involve symmetries. And so they don't capture these non-free operas, for instance. And I'm curious to understand why this is happening. And so this is a step in that direction. It's, as far as I know, the first kind of Cartesian closed category where these monads are non-symmetric operands.
Did you manage to get? So I was sort of an amateur finite group theorist at the time when I was a PhD student. I was in with Conway's crowd, and I had the ambition to get some finite group theory into theoretical computer science, but I only, you know, the work that you mentioned only ever involved symmetric groups. Did you get any more interesting groups arising?
I mean, I don't, not yet. But one thing I want to do is to take a look at the interpretation of lambda calculus in here and see what is the associated groups tell you about the beta reduction or beta reduction, say. I don't know. This is to be investigated. For the moment, I don't know.
Very good.
Okay. Any other questions? Maybe I have a few myself. So this notion of a linear species with a kit, how does it compare to the notion of quotient container of Håkon Gülterud? Because he did something very similar by listing these stabilizer groups by hand, so to speak, and just carrying them around in the construction.
So I don't know this where you're referring to, so I cannot comment on that.
Okay, let me put.
But is he building a Cartesian closed category?
I don't think so.
Okay, so that is a comparison.
No, but I think that's just because he didn't get so far. I mean, that was
I
his
see.
master's thesis. I
see.
think. Okay, I put his name in the chat.
I will look at it later because, yes, I would like to know. I mean, these kits, what they do is to control the degree of stabilization that you are allowed in your container, if you want to call them. Or
Yes.
yes.
I mean, there's something very similar happening right now in Petrinet theory. So John Baez and Fabrizio Genovese and Mike Schulman and Jade Master, they made some kind of Petrinets where you by hand put in all these stabilizer groups. So, well, they write it in a fancy way as a pre-sheaf on a groupoid, but if you look at it in terms of pictures, it is precisely about indicating for each transition in the Petrinet, you indicate the stabilizer groups that you sort of want to, keep track of, or how much symmetry you allow.
Yeah, so this is exactly doing that.
Okay. Then I have a question about terminology. When you say linear species,
yes,
where does the word linear come from?
Oh, this is in the species book. This linear, and also in Andres' first paper. The linear species are the ones that are defined on finite linear order and increasing bijections.
Okay, I think they also call them L species.
L species, yes, but they say L in brackets linear. So.
Okay, I see. Because I think they also, at least the extensions, they also call flat species.
Yes, sometimes I've seen that terminology as well.
Yeah, thank you, Marcello, for referring to my paper, but I think maybe linear species, I used that, this is like 40 years ago. I think today it's kind of confusing, right?
Yes.
Because it could mean species with value in maybe in vector spaces, or maybe, I don't know.
Yeah, so, that's true.
Yeah, but it's okay. I mean,
I'm happy to change the terminologies. Not
okay, yeah.
No, it was just curiosity.
I wonder, did you, if you take the symmetric group about the Boolean algebra associated to a group, what is the Boolean algebra associated to the symmetric group, sigma n?
So I have not calculated that one. So I calculated many. I don't recall calculating that one. So
okay,
I'll send you a mail tomorrow with the calculation.
For example, the first one would be the symmetric groups on 3 letters or something like that.
Yes. So, but that is 6 factorial. So I expect it to be the 4-element Boolean algebra.
Okay.
Yes. So that's what will be.
Okay.
Yeah, so maybe I would conjecture out of the blue, but from experience, from actual calculation that I have done, that it would be the highest power that fits into the n factorial. You see what I mean?
That's interesting, because it would be nice to know if this notion had been considered by group theorists, or
Yes, I've been searching. I asked various people. I have not got any feedback about that. I have not seen this construction elsewhere. I don't know deeply if it says anything about the group structure, and if it does, what it says. So at the moment, it's a bit mysterious to me.
Yeah, but it's an interesting invariant in some sense.
Yes, yes, it's an invariant, but I don't know what it's telling me. And even I have not calculated many canonical frames. And those should be, Hating algebra should be interesting as well.
Okay.
Yes.
Okay, but yeah, I had many other questions, but I think now we have to move on. So maybe you can unshare, Marcello.
Sure.
Thanks, Marcello.
No, thank you, Andre. Thank you, everybody.
And coming up next is Rune Haugseng. Are you there, Rune?
Yeah. Let's see if I can figure out how to share today.
Okay, that looks good. I think you should just go ahead, please. So it's a pleasure to welcome Rune Haugseng, who will talk about polynomial monads and Segal conditions.
Okay, well, thanks a lot for asking me to speak at this workshop. I guess I will thank you slightly less if the talk than I would if the talk wasn't at 10 p.m. on a Friday night. But right, so I want to talk about this work on a variant of polynomial monads that connects to homotopical algebraic structures defined using Segal conditions. So this was a joint project with Hongyi Chu. So let me start by trying to explain what I mean by the words in the title. So I'll start with telling you what I mean by polynomial monads in this setting. So first of all, this is in the setting of infinity categories. So I'll start with S being the infinity category of spaces or infinity groupoids or homotopy types. And then if I have a map of spaces f from x to y, it induces an adjoint triple of functors between the slice categories, spaces over x and spaces over y. I have the leftmost functor f lower Schritt given by composing with f, and then that has a right adjoint f upper star given by pullback, and that has a further right adjoint. This goes this way, of course. F lower star. And one way to define a polynomial functor in this context is to say that it is one that can be written as a composite of functors of these three types. But you can give a more intrinsic characterization of what a polynomial functor is. And this was proved in my paper with David Gepner and Joachim Koch in this infinity setting. So the functor f from spaces over x to spaces over y is polynomial if and only if f is accessible, so it preserves kappa filtered colimit for some kappa, and preserves I like to say weakly contractible limits. but equivalently you can say like arbitrarily like wide pullbacks. And then a polynomial monad on spaces over X is a Cartesian monad. So the unit and multiplication are Cartesian natural transformations in the sense that the neutrality diagrams are Cartesian squares. Cartesian monad such that the underlying functor, the underlying endofunctor is a polynomial functor. So I can tell my computer fan is making some noise. Is that disturbing? Or I could try and put on a headset if that would.
I think it's okay.
You're not as demanding as my calculus students, I guess. So, right. But, well, so having written these definitions, let me also say sort of the example of such a polynomial monad, coming from most of this work with David Joachim. Is that you can regard infinity operads as corresponding to what we call analytic monads, which is the polynomial monads with the further property that the functor should preserve shifted coordinates, not just be accessible. So we can regard infinity operas as a class of these polynomial monads, which I guess was explained in the Gebner's talk earlier in the week. But okay, so if you write the definition like this, you can say, well, these conditions for a functor and this definition of a polynomial monad didn't really use specifically that we were on this slice spaces over X. So, I mean, just as an abstract generalization, you could consider these conditions on a more general infinity category, or factorization of polynomial functors and monads. Just as abstract definitions, and more generally than just for slices of the infinity category of spaces. Well, fine, but why? Well, or in particular, one generalization you could look at which is the one we're looking at here, is for pre-sheaf categories, or well, it will be convenient to write them covariantly most of the time. So functors from some small infinity category I to spaces. And this slice category of spaces you can show is equivalent to pre-sheaves on the space. So this is a generalization of the previous notion. The spaces over X is equivalent to functors from X as an infinity groupoid to the infinity category spaces. So this generalization would include the previous case. So, okay, this is some abstract definition. Why should you care about this? Well, this is the idea that I want to try and explain, is that this notion of polynomial monads on pre-sheaf infinity categories turns out to be closely related to kind of homotopy algebraic structures. Homotopy coherent, maybe more precisely. That can be described by what I'm calling Segal conditions. So that's the next thing I want to introduce, is what I mean by talking about Segal conditions. I'll first give the kind of abstract definition and then to look at a couple of examples. So we define the structure that we call an algebraic pattern to be some infinity category that's equipped with, first of all, a factorization system where every map, say f to O prime, should factor uniquely up to equivalence into first first a class that we just call the inert morphisms, and then something we call active morphisms. So these are just labels for the two types of morphisms in the factorization system. And it's also kind of convenient to use some random notation on the arrows to indicate that they are inert and active. So we ended up in the paper using these notations for inert and then this squiggly arrow for active. That's kind of just, just a convenience to indicate which is which without meaning to really suggest anything about the nature. And then we can look at the subcategories where we have only inert and only active maps. Now I'll call those O inert, O int, and O act. So that's the first part of the structure. And then the second part is a full subcategory OL inside of O inert. And we call the objects of this full subcategory the elementary objects. And then, given the structure of an algebraic pattern, we can define one kind of Segal conditions for this pattern. So we just define it when we're looking at these structures in spaces, and that's what's relevant for this talk. So I'll say that a Segal O space is a functor from O to spaces such that for every object O in O, we have, if I look at the value of f at that object, I get a map to a certain limit of elementary objects. So I take OL under O to be defined to be this fiber product, more precise. So I look at inert maps from this fixed object O to the elementary objects. And then evaluate F. So I get this map, and I ask for this to be an equivalence. Another way to phrase this is that if I restrict F to the inert subcategory, then that is a right Kahn extension of the further restriction just to the elementary subcategory. So if I ignore the active morphisms, then F is only depends on this subclass of elementary objects, but then the active morphisms are added on top of that, and then the Segal condition doesn't tell you what they're supposed to be doing. So they're kind of right. So the inert morphisms in this definition are going to acting to tell you how the value of F should decompose, whereas the active ones are the ones to tell you what the algebraic structure is doing. Okay, maybe this will be clearer if I describe some examples. So the first is can take F star to denote the category of finite pointed sets. And it's kind of notationally convenient to just think about a skeleton of that, where we have the objects being the finite pointed sets 0, 1 up to n, pointed by 0. And then a map here from n to m is inert if all it does is send things to the base point, which you can phrase as saying that if I look at the pre-image of something that was not the base point in M, then that pre-image has size 1. And it's active if it doesn't send anything to the base point, which is to say, well, except for the base one, which has to go there. So it's active if the pre-image of the base point 0 is just 0. So then this defines a vectorization system. And then we can take the elementary objects to be just the single object 1. And if you work through this definition of the Segal F star space, you get that this is a functor from F star to spaces that takes on Fn. Well, you can check that this n has exactly n inert maps to 1. So this is the product of n copies of f of 1. And so this is exactly what Segal called a special gamma space. And he introduced this as a model for homotopy coherent commutative algebras. Or if you like, the infinity algebras. So this work of Segal is why these things are not being called Segal conditions. So another example is to look at the category delta, the simplex category, so the category of non-empty finite ordered sets. And again, it's kind of useful to have a skeleton where we just have bracket n, the object in bracket n, which is the ordered set of 0, 1 up to n. And then this is a factorization system. Well, where map F from N to M is inert if it's the inclusion of a subinterval, which we can phrase as saying the value of F at I is the value at 0 plus I, so this includes the interval between its two endpoints, and it's active if it preserves the endpoint, so F of 0 is 0 and F of N is N. This, if we look rather at delta op, then we can look at two different pattern structures in that. So the simplest one, we would take the elementary objects to be just bracket 1, and we get a Segal condition that is basically what it was in example 1. So load up the space with this notion of elementary objects would be a functor in delta op spaces such that the value of F at N is product of N equals F1. You can check this encodes a homotopy coherent associative algebra. But we can also look at another structure where we have as the elementary objects both 0 and 1, and then this elementary category will have two objects with a parallel pair of morphisms between them, like this. And now a Segal delta op space should have the condition that the value at N is an iterated fiber product of F of 1 over F of 0. So this is this is exactly what RESC calls Segal spaces, which is one way of describing the algebraic structure of infinity categories. So yeah, let me more briefly mention a couple of other examples. There is a category theta n op that I believe was first introduced by Segal. And this can be used. Well, you can put this pattern structure on that and use this to get a description of infinity n categories. And that's well, the way this is phrased is due to RESC. I guess a lot of these ideas were also looking back to Forsberg, let me write his name as well. And then we have the so-called dendroidal category of Awodey and Weiss. It can be used to describe infinity operads. And the way that they come out in this Segal condition framework is was first introduced by Sasinski and Awodey. And then there are various kinds of categories of graphs that have been constructed by Phil Hackney, Marcello, and Yao. That different variants that you can choose to describe infinity operads, cyclic infinity operads, or modular infinity operads. Right. So the point is really, well, we won't find an example as any infinity operad in the sense of Lurie's book. Can be viewed as one of these algebraic patterns. So, right. So the point is really just to say that there are all these different kind of homotopic algebraic structures that can be described using Segal conditions. And so you might ask, well, why is that, or which structures can be described with these kind of Segal conditions, and how, is there any canonical way to do it? And it turns out that you can answer this question by relating these structures to polynomial monads. So maybe I'm going to start with the kind of more straightforward direction, which is that you can get, if you have a nice pattern, you will get a polynomial monad from it. So let me write, if O is one of these algebraic patterns, let me write Seg O of S for the full subcategory of those functors from O to S that satisfy, that are Segal O spaces. Then there's kind of an underlying object for this. I can first restrict to from O to the inert subcategory, and then what the Segal condition says there is that if I restrict to functors from all the elementary objects to spaces, this is an equivalence with inverse given by right Kahn extension. So if I label the inclusion of OL in O int as I, and the inclusion of that into O as J, then this functor is J upper star, and this is I upper star with inverse the right Kahn extension functor I lower star. So I want to think of this as being kind of the underlying presheaf of a Segal object. So let me call this UO. And then you can show that UO is always a monadic right adjoint. And the left adjoint is given by, well, we start with functors from OL spaces. Well, we have this inverse functor, which is the right Kahn extension to go to C. And then we want to apply the left adjoint to J upper star on the level of presheaf category. So the left Kahn extension functor J lower shriek, which goes to fun O spaces. And then this inclusion of Segal O spaces in the functor category has just abstractly a left adjoint by, from the fact that this is like always an accessible localization of the presheaf category and so on. So there is some functor L that is a left adjoint to that inclusion. And so just formally you get that this is the left adjoint. But this is just some kind of abstract localization functor. So if you want to understand this monad, this abstract localization is in the way, and so what we do is to just consider those patterns where we don't have to do that. So we say that pattern O is extendable if this Kahn extension functor lands in, for an object in Seg O int lands in Seg O. So then this left adjoint is I'll call FO for free Segal O space, can be written as j lower shriek after I lower star. And we can actually give pretty concrete conditions that are necessary and sufficient for our pattern to be extendable in this sense. But I'm realizing I included way more material than I should have, so let me definitely not say anything about that. But the point then is that we have an explicit formula for the value of this free functor on, say, some elementary object E, namely, this is the colimit over a certain infinity groupoid O of E. This is the infinity groupoid of active morphisms to E of the limit over. So this is for such a morphism as of O, we take the limit over OL under O. And this category has objects inert maps to some elementary objects B prime, and we take the value of phi B prime. So it's some limit, some colimit, and the kind of key point is that this colimit is over an infinity groupoid. And then from that, right, let's say we have the monad, which is the composite of UO FO, which I call the free Segal O space monad. And what we show is that if you have an extendable pattern, then this monad TO is a polynomial monad on this functor category from OL to spaces where OL is not necessarily itself an infinity groupoid. So, in fact, this construction you can extend to give you a functor from our extendable algebraic patterns to polynomial monads. Then so this is one direction, and then the more surprising direction is that you can actually go back. You can start with the polynomial monad and actually define the canonical pattern associated to it. And so yeah, I think I will just write the definitions, although of how you get this pattern, although it's maybe not, well, I guess there are two stages to this. And the first part of this is basically it's an infinity upgrade of work of Weber. But okay, we can make the following definition, which is maybe not so enlightening just on its own, but well. So let's say we have T some polynomial monad on functors from I to spaces where I is some small infinity category. Then the fact that it's polynomial tells you that implies that this is a local right adjoint, which means that if we view T as a functor from IS to from IS over the value of T at the terminal object has a left adjoint. which I call L star. Then we can use this L star to define a certain subcategory, which I call U of T op, which lives inside fun IS. We define this to be the full subcategory on the objects that are of the form L star I for some map I to T point where I lives in the indexing category I up via the unite embedding. So and then we can look at the free algebras on the objects of this subcategory. I'll call that W of T up. So this is inside T algebras and fun and free algebras on U of T up. Okay, the reason for making this definition is the following theorem, which is called the nerve theorem. So again, this is just an infinity variant of existing results. I believe first, so for one categories, first proved by Leinster, and then generalized by Weber, and for three use is really Dagger, Milius, and Weber. So in this for such a polynomial monad, we can describe the infinity category of T algebras with the right adjoint functor, forgetful functor to from IS as pullback, where at the bottom we have the functor of right Kahn extension along, well, I guess I didn't say that this is true, but it is true that this category U of T will contain the image of the unite embedding, so there is an inclusion, so what I'm calling IT. And then we have the free functor, which I'll call JT, which goes from U, W. So we have this right Kahn extension, which is an inclusion for the faithful. And here I put from W of T S. And this is JT upper star. So the theorem is that this is a Cartesian square of infinity categories. And for the left adjoint, the mate transformation commutes is an equivalence. The mate square commutes. So JT lower freak and the left adjoint on the right here, composed with IT lower star, is the same as this new functor composed with the left adjoint FT. And this is new, and this is the restricted unita embedding along the inclusion of W into algebras. So if you look at this, this almost says that alg T is is described by an algebraic pattern that looks a lot like it. It's we're saying that we want to say that I is the elementary objects. This is the pattern, and this is the inert subcategory, and then this full subcategory is, because it's the pullback, it's exactly the subcategory of functors from W of T whose restriction to U of T is right constant from I, which is a lot like one characterization of the Segal O spaces for a pattern O. and yeah, so this, yeah, we can characterize this as saying that the monad T almost comes from a pattern structure on W of T. The only issue is that this U of T need not be a subcategory of W of T. It need not include all the equivalences. So U of T may not contain all equivalences in W of T, and so it's not, well, it doesn't give you a factorization system unless you do something about that, because in a factorization system, both classes have to contain the equivalences. And it turns out that we can fix this, and so if I look at a map ftx to fty, then I can use this this functor L star to get a factorization of this phi, which is in Weber's terms, and we use this language too. We call it the generic free factorization. But I mean, this is adjoint to a map from X to Ty, and then the map from Y to a point to the point gives you a map to like this. This is T of the map from Y to the terminal object, and then so this is a map in over T of a point, and therefore this is adjoint to, this corresponds to a map from L star X to Y, and then from that and the adjunctions, you get that this phi factors as ftx to ft L star X to fty, but the second map is this psi, and this is ft of psi. So we'll say that phi is inert if from ftx to ft L star X is an equivalence, and active if the other map is an equivalence. And what we prove is that inert active maps give a factorization system on this W of T. So by taking the free maps and closing them up under equivalences, we actually get a factorization system where, and therefore we can define an algebraic pattern if we take the elementary objects to be the free algebras on the object of I. Okay, and then one can show that this pattern W of T is extendable, and it kind of describes, well, it's very closely related to the original monad in the sense that we have the following square. If I look at the T algebras, then the monadic right adjoint UT actually factors through functors from WFTL. And this is equivalent to Segal objects for WFT. And this is equivalent to, well, by definition, to Segal for WFT inert. So if I kind of replace my monad on functors from I to 1 with this other category, which like in a sense kind of adds more equivalences that we didn't have here, then we actually get that this monad is coming from this pattern on WFT. So this construction actually you can also take as functorial. It gives a functor from polynomial monads and pre-shift categories to patterns. We can actually, so we have functors in both directions, and we can actually characterize the images quite explicitly. So let me try and explain that very quickly in the last few minutes. So these are the classes of saturated patterns and complete polynomial monads. So maybe we'll start with the complete. So polynomial monad T is complete. This means that it actually did act on the right space. So we have an essentially surjective functor from I to WFTL, kind of by definition, and we say that it's complete if this is an equivalence. So right. Like let me say the complete polynomial monads are a localization. Full subcategory of complete polynomial monads is a localization of polynomial monad of that of polynomial monads. And there are exactly those monads that come from patterns. The other direction, yeah, okay. So we say a pattern O is, this is first some kind of very minor technical condition. We say that it's slim if every object admits an active morphism to an elementary object. So you can kind of just ignore this. I mean, if you have a pattern and it doesn't satisfy this condition, you can just throw away those objects that don't have an active morphism to an elementary object, and you still get the same monads. And sometimes whatever that, whatever didn't satisfy that wasn't really contributing anyway, so you can just throw it away. And we say that a slim pattern is saturated if it's slim and extendable, and and the Segal condition kind of holds as a limit condition in O. So for every object O, O is equivalent to the limit in O for every object X in O, x is equivalent to the limit of the Segal category OL x. So the Segal condition holds as the limit condition in the pattern itself. That's what I'm trying to say. And then we can show that saturated patterns are exactly those that arise from polynomial monads. And give a localization of slim patterns. So these constructions that we have in both directions give you a way to kind of improve your monad to a complete one and your pattern to a saturated one. And let's say this is the final theorem, that we have an equivalence between complete polynomial monads and saturated patterns. So the algebraic structures that can be described by Segal, extendable algebraic patterns are exactly the ones that that are given by polynomial monads, and so for such a for such a structure, there is a kind of canonical pattern, namely the unique saturated one. Okay, I'll finish here. Thank you.
Thanks a lot. Questions, comments? Well, I can start. Should we think of complete as like resc complete if it were just a category?
Yes. So like I guess there are two ways in which you can think of the analogy of, like, maybe one is just that it is kind of a similar notion of having the correct space of that it's acting on, but you can also more directly think of, well, you can think of any Segal space as giving you a polynomial monad on its zeroth on spaces over its zeroth space, and that monad will be a complete monad if and only if the Segal space is complete.
Okay.
Or more generally, if you look at like dendroidal Segal spaces, then they give you analytic monads via the construction from our paper, and then that dendroidal Segal space will be complete if precisely when the corresponding monad is complete in this sense.
Okay, thanks.
Maybe I would like to ask a question.
Please.
It's a very nice talk, very nice work. So if I understand it correctly, this equivalence, this theorem, is valid in the context of infinity categories.
Yeah.
And is there a similar theorem in the case of one categories, or this is somehow the theorem in the case of infinity categories is somehow better than the theorem that you may formulate in the case of one categories?
I haven't really thought about the one category version, I guess. I mean, I guess the most basic issue is that not, many things that are polynomial in the infinity world are not polynomial if you just work with one categories.
Okay.
Depends
Yeah.
how you have this.
Because the theory of analytic functor somehow works better in the context of infinity categories by the work of Gepner and Koch, because an analytic functor is really just a polynomial functor. So I was wondering if the same thing is happening here, because anyway you're using polynomial functors, but
yeah, I mean
in some kind of hidden way they are analytic functors in some sense, right?
Well, the analytic functors will be contained in, well, you're right. So in the infinity setting, the analytic monads will be a subclass of the polynomial monads that I'm looking at here. So
okay. Okay. Well, it's a very beautiful theorem. Thank you.
It involves way too many definitions to give a good talk about it, unfortunately.
I have one more question. Once you have the pattern associated to, well, let's say a complete polynomial monad, can you use the pattern to write down some kind of bridge shape diagram?
So I want to say that you can do, well, I guess any polynomial functor in our sense should so, and I want to say you can do something like any, you know, I mean, you're still looking at like a local right adjoint functor between pre-shift categories, like you can. I couldn't find any like nice conditions to say when such a diagram gave you a polynomial functor. So I think you can go in the other direction and get get kind of a polynomial diagram of some sort of categories. But yeah, I'm not sure how to go in the other direction. And this, yeah. I guess there's a similar issue with this. You know, we have this relation. You might ask, well, can we?
Oh no, we can't. Are you writing something?
No, I was going to say, you might ask, well, what if we remove complete here? Can we put something on the side? And this is to do with, I don't really know anything nice to say unless you restrict to monads on slices of spaces, like in the classical case, because it's very hard. I don't have any conditions to say like what, you know, you can ask, you know, if this is a polynomial monad, when is this composite with some essentially surjective functor from I to WL a polynomial monad, and I don't know when that happens. So.
Okay, thanks.
I wonder if I can ask another question.
A quick one.
Oh yeah. The notions of Segal space is also, I mean, there is also the notions of complete Segal space. Is there anything like that in your theory? And it's complete.
It should be something that's more specific to each structure, whether you have a notion of completeness and, you know, kind of is related to having a notion of fully faithful and essentially surjective maps that you want to invert. And so, like, if I go to the list of examples I had at the start, which I went to do very quickly, unfortunately, but so we have, you know, we have a notion of completeness from RESC, and you can kind of generalize this here and here, and then if you in these cases where the underlying structure isn't really a category, it's something like a dagger category, or what's the more general.
Okay.
I don't really know what is a good notion of being complete, and yeah. So okay. I don't think there's any general story, and like there are interesting cases that remain to be explored. But, yeah.
Okay, thank you.
Okay, then I think we should thank Rune again and move on. So thanks a lot. And then Rune, maybe you can unshare. And then we are ready for Fredrik.
Okay.
Looks good.
Looks good. Sounds good.
Okay. So, let's just start. So it's a pleasure to welcome Fredrik Nordvall Forsberg, who will talk about quantitative polynomial functors. Please.
Right. Thank you. And it's a pleasure to be here. So thanks very much for the invitation, Joachim and David. Really interesting workshop. So I'm going to talk about something a little bit more type theoretic again. But to mix things up, it's not going to be the type theory that most of us perhaps know, but something called quantitative type theory. So I'll spend a bit of time trying to tell you what quantitative type theory is and then what the connection with polynomial functors is. So, so to do that, let's put the focus in the right window. And then let's start with linear logic, because this is quantitative in the sense of Girard and linear logic. So, of course, in ordinary logic, we can prove something like this, that if I have A and I have A implies B, then I can derive A and B, right? And if you're a fan of Curry-Howard correspondence, then you might put in proof terms like this. And I've changed this and to a times just to really emphasize that we are doing some kind of type theory here, right? And the point is that we are, as we see, we're using this X twice in order to derive this result, right? But if we look in the real world, in quotes, real world, if I have an apple and I have an oven, then I can't both have an apple and a pie, right? I have to decide if I'm putting my apple in the oven to turn it into a pie or not. So this is what's called linear logic. So just to make a distinction between this and ordinary logic, let's change the symbol a little bit. So instead of an arrow here, I'm going to, oh, sorry. I'm going to change this to something called a lollipop. So this is the linear function space where I use exactly one apple to turn it into exactly one pie. And instead of and, I'm going to, or times, I'm going to write a tensor here, right? So this is called linear logic. And the point is that we are keeping track of how we're using things. So this is the quantitative in this sense, right? So this is, of course, a very silly example, a stupid example. But in computer science, there's also more serious examples of these things, where you can use linearity to describe I/O, because you can't really print twice to the same screen or something like this. You have to print exactly once, right? Or you can only send one message on a communication channel before it turns into a different communication channel because someone on the other side actually received your message. Or maybe you want to use this for memory management. So you know that you have exactly one reference to this memory, so you don't need to garbage collect it. Or you don't have to keep track of it if it's still there or not. So that's linear logic, and it has, since it's been around for, I guess, 30 years now. And it's always been the next up and coming thing somehow. Another thing that's been the next up and coming thing for a long time is dependent type theory, which you could see, if you want, either as the foundation for constructive mathematics as a logical system, or if you want, you could see it as a very fancy functional programming language where you can write these programs that we had on the previous slide, these proof terms, right? And the point is that as a type system, it's expressive enough to encode logical propositions into the type. So this is how you can do constructive mathematics in a functional programming language, right? So for example, you can say that the function head, which takes a list and gives you the first element of the list, well, this only really makes sense if it's a list which has at least n+1, which has exactly n+1 elements, right? You can't do this for an arbitrary list, but you can do it for an arbitrary list if you can encode the length of the list in its type. So you can't really say that head goes from list to A, but you can say that head goes from lists of length n+1 into A, because then you know you always have a first element which you can use as the head. And similarly, if you have a sort function and you want to be really precise about what this function is actually doing, then you can say that, well, it takes a list with n elements, and it's going to give you back a list, again with L elements, so it hasn't thrown away any elements or something like this. But it's not just a list, it's actually a sorted list. So you can encode what it means for a list to be sorted in the type system. And then just by looking at the type of this function, you know that it's actually going to sort the list for you, right? So this is almost a complete specification, right? So we haven't thrown away any elements. We have the same numbers. We can't just return the empty list all the time or something like this. That would be sorted, but not a very good sort function. So we know that we keep the same number of elements and they are sorted. So the only thing we haven't completely specified with this type is that the elements here are really the same elements that we started from, right? That this is a permutation of this list. Because I could still trick you by implementing a sort function like this, which takes a list, looks at the length of it, and then gives you the sorted list 1, 2, 3 up to n if you wanted. And that would still have this type, right? So it's always a trade-off how much you want to pay up front and put in the type versus how many guarantees you get. So you can have nothing, that's an ordinary type, or you can have everything if you're willing to pay a little bit more. So it's pay as you go in a way. So that's very good for functional correctness, as we've seen. So I can be sure that my sort function does the right thing, but we've lost this resource guarantees that we had from linear logic, right? So in a way, it would be very natural to try to combine these two different systems into one system where I can both have functional correctness, but then also strong resource guarantees that I'm not copying the world when I print to the screen or something like this, or I'm really communicating with my friends and not neglecting them and never sending them a message. Right. So it would make sense to combine linear and dependent types in order to get the best of these both worlds, right? But this is quite difficult if you think about it. And I think it is difficult on a more or less fundamental level. It's not just a technical difficulty, but also a philosophical difficulty, what this should actually mean. Right? So for example, if you have an identity type, so this is the type which encodes that two terms are equal, so it's the type version of the logical equality, then it normally comes with a proof or a constructor refl, which says that every x is equal to itself, right? But then already here you can ask, well, is this a linear function or not? Because the x here is occurring twice in the type. So it's not completely obvious that this should be allowed to start with. But of course, I mean, it would be ridiculous if we couldn't even prove that things are equal to themselves. And if you think about it, if this is a constructor, it's only really using its argument once, right? Even though it occurs twice here in the type. But it's not completely obvious if this should be allowed or not, even though it definitely should. And similarly, here's basically a variation of the same problem. If I have a function for division, so I take one natural number, I take another natural number, but I want my function to be total, so I also take a proof that the second one is greater than 0, so I can divide by it. Then again, we have the same thing, that this m here is now occurring twice in my type, right? So if you're really pure about it, you could say, well, this can't be linear because m is occurring twice. But if you think about how you implement this m is really different from this proof object, right? So again, I would say that this should be allowed to be linear, even though it's not completely syntactically obvious, right? And if we look at the sort function again, so you can actually upgrade it to something that's completely specified what it does. So now we take a list of n elements, we return a sorted list, and we return a proof that the underlying list of the sorted list is a permutation of the list we started with, right? And so here I'm going to use my list x's in order to produce my list x's prime, but then I would also like to afterwards prove that I have a permutation. So it's not at all obvious if this is linear or not, right? So partly because it's kind of occurring, well, it's not really occurring twice in this case. So this is a different thing, right? Where I'm using it to construct this thing, but I'm also maybe using it to construct something else. But if we actually want to deliver on this guarantee of combining the best of both worlds, then this is exactly what we would like to do in some sense, right? We really want to be able to prove things about our programs and not just keep things separate. So there's been some attempts to bring these things together. So the early attempts were based on a variant of linear logic called linear nonlinear logic, which dual intrinsistic logic and things like this. And the basic idea is that we take our context of assumptions and then we split it into a linear part and a nonlinear part. So here I can keep my assumptions that I can use freely. So these are nonlinear. And here I keep my assumptions that I have to use exactly once. And this is based on a junction models of the linear logic where you can go between these two different worlds. Right? And the point then is that when you form a type, you make it to only depend on the nonlinear terms here. So you insist that the linear terms are actually empty. So the good thing about this is that the question how to count occurrences in types just goes away because there are no occurrences in the types, right? Because I'm not allowed to form any types that depend on linear variables. So I don't have to count them. I only have things occurring in my types that can occur as many times as I want. So that question goes away. But on the other hand, you can't actually prove anything about linear terms, right? Because the way we prove things about them is by forming propositions as types about them. But I've just said that I'm not allowed to form any propositions about linear terms. So in a way, this is combining dependent and linear types by very carefully keeping them apart and making sure they never touch at any time, right? Which it's a great generalization of linear nonlinear logic, but it's not getting quite there in terms of really combining these two different systems. So let's look at another system which I think achieves this a little bit better, and this is called quantitative type theory. And the core idea here is that it's still possible to contemplate things even after we have consumed them. So even after I have eaten my apple pie, I can still think about how great it was, and I can prove that it was delicious, right? Even though I've already consumed it. And I can prove that it's delicious as many times as I want, right? It's different to contemplate than to consume. So that's a great philosophy, but how do we make it into a type system? And the core idea here is that rather than erasing things when we've used them, we record how many times we used them in the context. So for example, here for this silly derivation I have, since I have used X twice, I record that I used it twice. And since I'm using my oven once before I throw it away and buy a new oven, I record that I have one oven here, right? And the point then is that I can also have other things in my context that are not occurring. So for example, I could say that I have some, I don't know, I have some poison. And it's in my context, but I'm not actually using it to make my apple pie. So I can still, I put it in my context, but I'm recording that I'm using it 0 times, right? So then I can make my pie, and then afterwards, if I want, I can prove that there is no poison in the pie, but I don't have to use it. But why can I do that? Okay, sorry, let's go back to that point. So the important point is that when I form my types, I do that in a context where nothing costs anything. So it's a context where everything has usage cost 0. So that means that usages from forming types do not count. But let's get back to this point that what these annotations are. So they come from any semi-ring you want. So semi-ring are exactly the axioms you need. So good semi-rings you could use could be, for example, that you could take the natural numbers, right? That's a very natural way to count things. And it's a semi-ring, it's not a ring. So semi-ring means that there is no there's no negation for the plus here, right? So that's why the n is missing in the ring, no negation. So counting things from natural numbers, there's no inverse to plus, but we can add things up and we can multiply. Another good semi-ring to use could be something like I have 0 things, I have 1 thing, or I have infinitely many things. which again is a semmering, where basically whenever you hit infinity, you stay at infinity, right? So this is quite a practical semmering, because you can say that you have no poison, you can say that you're using your oven exactly once, and then you can still allow unrestricted apples if you happen to have access to that, right? So then you can include standard type theory into your type theory in a way, just by using the infinitely often modality. Okay, so why do you need a semmering? Well, if you look at the typing derivation for function application, so if I have a function f, which takes an x in A and gives me a b, which might be dependent on x if I want, and if I have an a in A, then normally I can apply f to A, and I get something in B of A. Right. But now let's put some context in. So if this lives in context gamma, and if this lives in context gamma prime, so normally I would have the same context here, but now I'm keeping track of how many times I'm using things. So I better separately keep track how many times I'm using things in order to make f, and how many times I use things in order to make a, right? And then when I make f apply to a, then I should add these two contexts, right? So I add all the usages from the first one to all the usages of the second one. So that's why I need a plus in my semmering. So that I can, okay, so I can extend this plus pointwise to the contexts, right? So I add up all the apples for f and all the apples for a, and then I get all the apples for f applied to a, right? But I could also say that instead of just having functions from a to b, I can also record how many times the function is going to use its argument. So I have a little row here which comes from the semmering, which says that this is a function which is going to use its argument row times, right? So if I now apply this function to a, that means that I have to make row copies of a in order to feed enough copies of a to f, right? So I have to multiply, this is the resource usage I need in order to make one a. So if I take row times that, which just means I multiply each occurrence in the context by row, then I get the usage I get in order to make row copies of a, right? So that's why I need the times, so that I can multiply usages in order to have more of them, right? Okay, and then I need a 0 and a 1 in order, yeah, I mean, it's just natural because it's a semmering. It's just not some random operations. And right, and in particular, I need a 0 in order to be able to talk about things that are free, right? Because now I'm saying that I can only form types by zeroing out the context, multiplying the context by 0. So that means that I can use everything as much as I want, because nothing costs anything, right? I can't make anything which is non-zero, but that's okay, because to make types, I only need 0 things. So occurrences and types are free, that's the point. And we can still prove properties of linear things, because that just means we still have the poison in the context, and then it occurs in the type where I can use it freely. And then I can hopefully prove things of it in a resourceful way, right? So I still need resources in order to make the proofs, but I don't need the resources to make the propositions that I'm inhabiting. Okay, so that's a very syntactic description of what's going on. You could also give a sound and complete categorical semantics for it, which is building on a standard categorical semantics for ordinary type theory that I think Steve is going to tell us about in 40 minutes time, which is called categories with families. So because this system here in a way is an extension of ordinary type theory with a little bit more annotations, the semantics here is an extension of the ordinary semantics with a little bit more annotations. So we are starting with an ordinary category with families. So let's introduce this step by step, because it's a bit of a mouthful. So we start by asking for a category C, which we're thinking of as our category of context and substitutions. So the objects here are the contexts, and the morphisms are the substitutions between the contexts. That's our intuition. Right. And then on top of this, we're asking for a functor from C up to set, which is giving us the types in a given context. So for every context, I have a set of all the types I can form in that context, right? And it has to be C up because that's how we apply a substitution. It goes backwards. And on top of that, we also ask for a collection of terms. So this says that whenever I have a context gamma and a type which makes X in that context, then I get a set of all the terms of that type in that context, right? And this again should be functorial. And you might think, okay, it looks a bit strange because here I've written something like a dependent functor, right? For every gamma I should have a functor. So in the original formulation by Peter de Beer, you notice that you can actually take these two things together. So you take the types and the terms, and if you pair them up, then you get a functor from C up to fum set. So fum set is the set in this co-parallel completion of set. But so you see that here that for every C I get an index set tie of gamma, and then I get a family indexed over tie of gamma. Right? So that makes it look a little bit more like an ordinary functor. Okay, so far we have a category, we have notion of types and terms, but then what makes type very special is that we also have a way to extend context, right? So whenever I have a context and I have a type in that context, then I can form a new context where I have the old context and I extended it with one fresh variable of this given type, right? And so we ask for this structure, and we make it unique by asking for it to have a certain universal property that maps into it or can be factored. So that's an ordinary category with families. So if we only have this, then we have a model of ordinary type theory, right? With no type formers. We have to ask for these extra. But so now let's see what we have to add in order to also get a model of quantitative type theory. So the first thing we add is another category of context, but this time the context should have these resource notations in them, right? So we're asking for a category L, which we're thinking of as the resource context, and again, substitutions as the morphisms between them. And because the types aren't formed in any special way, they're always formed in this zeroed out context, we don't have to ask for a notion of a resource type or anything like this. We're just reusing the types from here. Sorry, I should have said that every context here has an underlying context in the ordinary category, right? Which you intuitively get by just erasing all the resource annotations from the context. Right, so you can always take a resource context and produce an ordinary context. So we don't have any resource type. Okay, sorry. Starting to get in the structure of the context. So we had this multiplication before. So for every element of the ring, we'll have a scaling functor, which takes a resource context and gives us another resource context where we've intuitively multiplied all the resources by row. Right? So we just do this for every element of the ring. And similarly, we need to be able to add the contexts. So if I have two contexts, and importantly, if they have the same underlying context. So I form the pullback over for this underlying functor twice. So that gives me all the resource contexts that are over the same underlying context, and these I can add up in order to get a new context. So I can only really add things if I have annotations for apples in both of them, right? Can't have apples in one and pears in the other. Okay, so that's the additional structure we need on the resource context in order to make sense of the resources there. Right? Now, finally, we don't have any special types, but we do have special terms because we saw that the terms could also have annotations in them. Right? So this is very similar to the terms we had before, but of course we're using the resource contexts, and we're saying that we have a type in the underlying context, then we get a set of resource terms. And this has to be over the other terms. In other words, if we apply the u to everything, then we should get something in here, right? So everything should always be over the standard thing. And in the same way, we should also have a resource context extension for every annotation. So if I have a resource context that I want to extend, and I have a type in the underlying thing, and I have a resource annotation for my new variable, then I get a new context, which I get by extending these things, right? Which again should come with a universal property, etc. And it should be over this one. Okay, so that's a bit of a mouthful. But hopefully once you internalize what an ordinary category of families is, it's not so hard to see that this, again, is more of the same thing, right? And there's a theorem by Atke, which says that this is, I don't think he actually states it like this, but it's sounder complete semantics for QTT. And it's complete because the term model is an instance of this. Okay, but it's also good. So that's a nice framework, and it's familiar if you're familiar with categories with families, but it's also nice to have some concrete models in mind, right? So let's see if we can think of some concrete models. So the first one you can think of is that if you take any category with families, then you can just reuse it also on the resource level and ignore all the resource annotations. And this gives you a model of quantitative type theory. Right? So the system is designed so that it's really a refinement, but it's not mandatory that you make any use of this extra information. So at least this gives you a great wealth of new models, or old models rather, that you can import if you want. Right? So it's definitely not a trivial notion. But let's look at a more interesting example. So this also takes a little bit of a setup. So we have our semi-ring, and now we're going to look at linear realizability models. So we have let's also fix a so-called linear combinatory algebra. So this is a set A, which you're thinking of as programs. And we're thinking of them as programs because it comes with an application operation, which takes two programs and applies the first one to the other in order to make a new program. So this is like an untyped programs, right? So the point is that we want to keep things easy and untyped here in the semantics, so we don't have to worry about the type dependency here. We have the syntax for that. Okay, so we have the programs, we have the application of one program to another, and we also have a duplication operation, which is indexed by the row from the semi-ring again, right? So this intuitively means that I can take a program and I can make row copies of it in order to get the resource information in. And then in order to actually write programs, we are asking for all of these combinators. So there's BCI, which is basically combinators for linear, the linear lambda calculus, so just like S and K and I, if you want, gives you the ordinary lambda calculus. If you have B, C, and I, and this time I is not derivable from the other ones, this gives you the linear lambda calculus. So this means that with S and K, you can make any lambda term. You have this combinatory completeness. And with B, C, and I, you can make any linear lambda term where you're using the argument exactly once, right? So using combinators is just a way to avoid talking about names, really. But we have the same expressivity as if we just use the linear lambda calculus. And then the rest of these combinators, the K, W, D, delta, and F, are there to control the duplication operation. So the K is a good example where the K combinator says that if I have so I always have to have a context X, but then if I have 0 copies of Y, then I can just discard these 0 copies in order to just keep the X. Right? So it's like the ordinary K combinator, except I can only do it when I have 0 copies rather than in general, because I really want to keep the linearity in mind. Okay, so if I have such a notion of a linear combinatory algebra, then we can form assemblies over this. So this is our notion of realizability, and an assembly is given by a set and a realizability relation, which relates programs and elements of the set. So I'm thinking of the set as my real data, and then I have my down-to-earth realizers that make sure that I can actually compute with these things. Right? And so that's what realizability normally does, but now they're also making sure that I compute in a linear way, because I have a linear combinatorial algebra. So this way I can relate ideal sets and linear programs like this. So this is what makes sure that my model really is something modeling linearity. Right? And the morphism between two of these things is a function between the underlying sets such that there exists a program in the combinatorial algebra which realizes f. So that means that if A realizes x, then if I apply AF to A, then I get the realizer for f of x. And note that I'm just asking for this to exist. It's not part of the morphism. So equality of morphisms is just equality of the functions. I can have many realizers realizing the same thing. Okay, and then if you have one of these, then you can take your assemblies to be your linear contexts, and you can take your ordinary context to just be sets, and you go from one to the other, they just take the underlying set of the thing. And if you want to be more concrete, which is also good to be sometimes, you can take your linear combinatorial algebra to be the linear graph model. So this is like Scott's graph model, but the application is linear. So it's the power set of natural numbers with a special application so we're representing linear functions or the graphs of linear functions. It's a nice concrete model to think about. Okay, and one more model that I like is if you look at relational models, and then why not build them on top of the realizability model so you get the right linearity. So you can look at reflexive graphs of assemblies, and you can look at reflexive graphs of sets, and there is an obvious forgetful functor from one to the other where you just forget about the realizability information. And the reason I mentioned this model is that it can give you some interesting parametricity properties for free. So you can show that all sorting functions that are linear are actually permutation preserving from the outset. So using this model, so you can get some nice things for free. But okay, I'm mostly going to focus on this second model for this talk. Okay, so there are some types we can form in QTT. So some of them we've seen already. So we have the dependent functions, which is using its argument row times. And similarly, we have dependent pairs, where I have row copies of the first component. So this is like a sigma type, but I'm really keeping track of how many times I'm using the first component, and then I'm using the second component once by default, right? But if I want more than once, I can always multiply my context to get more copies. And if this is like a dependent tensor, then it also has a unit, which is also the unit type. And using these together, I can form something like a bounded exponential, where I define bang row of A to make a dependent pair of row copies of A, and also use the unit. So I have row copies of A, and then I have some information that I can throw away because it's the unit of the tensor. Right? So this way you can encode bounded exponentials if you want. You don't have to add them separately. Okay, and we also have the terminal type, which you might think is the same as the monoidal unit, but it's not. And one way to see this is to look at the realizers in the model. So the semantics of the monoidal unit is going to be a unit set. And then we're going to say that X realizes star if and only if X is exactly the I combinator. So this means that it's easier to make functions out of this type because we know exactly which realizer we get, right? And it's something we can use. It's something we can apply to anything to get anything. So that way we can escape out of this tensor to just the first component, for example, because we know what a realizer for the second thing is. Whereas the interpretation of the terminal type has the same underlying set, but now we're saying that X realizes star if and only if true. So anything is a realizer for this star, which means that it's really easy to make a function into this set because you don't have to, there's no condition on what your realizer should do. You just have to say produce anything. But it's quite hard to make functions out of it, right? Because you don't get any information about the realizer you get, but you have to maybe produce something else. So you couldn't produce a function out of this if you replaced this with a terminal one. So here you see the difference that arises from linear logic compared to ordinary logic. But these are not the same thing in linear logic. Okay, and then you also have the additive disjunction, which is like a coproduct that we're used to. But we also have the additive conjunction, which is not like a coproduct or a tensor. It's something where you have to make both pairs, but when you take it apart, you only get one, but you get to choose which one, right? So when you take a coproduct apart, you only get one, but someone else chooses which one you get, right? Here you only get one, but you choose which one you get. So we'll see that this could be interesting later. Okay, so that's some basic types, but what about adding data types to this system, right? So of course, we also want to program with trees, lists, natural numbers, and all these things, etc. Right? So we could try to add them ad hoc by writing down rules for them, etc. But then how do we know that we have the right elimination principle? Right? How do we know we actually added the right thing? We have the models, so maybe that could help a little bit. It has to be something that we can interpret in the model, but it's still quite tricky, right? So instead, I think it would make sense to take a principled approach and use polynomial functors to see what the right thing should be, right? So let's do that. So here's how you would write an ordinary polynomial functor in ordinary type theory, right? So only thing is I've written the sigma in this funny way infix instead. So now if I want to turn this into something that makes sense in QTT, well, I will just turn the sigma into a tensor, a dependent tensor, and I will just turn the function into a linear function, right? And now this makes sense. And you could say, well, how do you know that you want a linear function which uses this exactly once? Well, if you want something else, then you can always take P of S to be bang rho of P prime of S, right? So you can add in more multiplicities if you want. And in the same way, if you don't want exactly one thing here, then you can just take S to be bang rho prime of S prime. So there's no loss of generality to just have one of these. Okay, and then you can prove that this is a functor, but you have to say a functor on what? Well, it's the category of closed types and linear functions. So the objects are types, and the morphisms are linear functions between the types. Right, so I'm saying that if you have a linear function, then you can define a linear function between the containers, just like you normally do, right? And if you think this is a little bit too restrictive, then you can move to types over a fixed context, but then you have to also include which context the morphisms are in as part of the data, because when you compose morphisms like this, then you're actually adding the context here, right? Which is different from what you would do in ordinary type theory, where you can just have a fixed context. And the identity, importantly, is uses the context which uses no resources. Right, and then this functor here actually preserves the context, so it's not doing anything to it. It works in the same context. Okay, so we have a category, we have a functor on it, so we can consider the category of F algebras for this. Okay, so it makes sense to ask for initial F algebras, right? And if you look at the model, the realizability model, then I know how to construct initial algebras in these models if the polynomials are finitary. I don't know how to do it for arbitrary polynomials yet. So that's something I would like to look more at. And the idea is not too complicated, I think. So you have to construct an underlying set, and you just do this as you normally would in the meta theory. So for example, if your functor is 1 plus x, or unit O plus x, then the underlying set of the initial algebra is the natural numbers. And then we have to define what the realizers are, but we can do this by induction on the elements in the meta theory, because we know exactly what the elements are here, right? They're coming from this initial element in meta theory. So for natural numbers, for example, we say that the realizer of 0 is 0, and the realizer of n plus 1 is the pairing of 1 and r of n. We use some pairing function on natural numbers. And then you say that x realizes t if and only if x is exactly r of t. So that means that when you define functions out of this thing, you know exactly which realizer you're getting, which makes it not too hard to do this. And then you can check that the constructors and the mediating map are realized, again, by meta induction on the things you have. So we can construct these things in the model, which is some relief at least. So what about the elimination principle? So, because that was just for initial algebras, right? So let's say that we have this functor, and let's say that we have some algebra C, which goes from f of w to w. So w is the carrier, and I have some algebra map. Then I would like to prove that I have an elimination principle if and only if this algebra is initial. So the first thing that's the problem is that it's not so clear exactly how to formulate the elimination principle, right? Because we have these choices of which things we should use how many times. So it's probably clear that because everything in our category is linear, we should probably get something which is linear, but it's not at all clear to me a priori how many of this we should have, how many of this one, and how many of this one, etc. But we see that if we derive this from the initiality principle, then there's only one choice that will work. So let's see if we can carry out this program where we start from assume that we have an initial algebra, and then we get the elimination principle. So we do it the way Christina showed us yesterday, where we form the traditionally the sigma type and make that into an algebra. But now we don't have sigma types. We have dependent tensors, so we have to use that instead. Okay. And then because it's an algebra, we get a map from the initial one. Like this, such that it commutes. Okay, and then what we normally do is we compose with the second projection, but then we see that we can't do this for any dependent tensor here, because we can only do the second projection if we are promising to have 0 copies of the first element, right? So in order to get the second projection, we really have to have a 0 here. Otherwise, this is not a linear function. So that kind of resolves what we have to do here. That means that we have to have 0 of these. And right, and in order to actually make this algebra, then we see that we need one of these and one of these. So the fact that we wanted to get this from the initial one has resolved that question for us. This is the only elimination principle that makes sense if you're trying to make this into an algebra. Okay, so we compose with the second projection, and we get something that looks kind of right, except that we don't know that Q holds of X, we know that Q holds of something else. So we have to prove that this something else here really is the same as x. And we do that by putting in the first projection here and proving that that is an algebra morphism, that is, this commutes, because then by uniqueness, this algebra morphism here, this composition must be the same as the identity, which means that this must be the same as the identity. Okay, and then you could say, well, how are you allowed to use the first projection if you have 0 copies of the thing? But I'm allowed to do that because I'm just mucking about in the types now, right? I'm only trying to make this type be something else. And when I'm mucking about in the types, I'm in the 0 context and I have unlimited use of things. Types are free, right? So I can do this. Right, so then by uniqueness, you get something that has the right type. And we have proved that if we have an initial algebra, then we have induction. And the other direction works the same way as usual. There's only one problem with this, which is that it doesn't quite work as you would expect. So normally, you would generate, another way to generate polynomial functors is to inductively generate them from identities, constants, and close under plus and times, and maybe exponentials if you want. Right? Because we have this container normal form theorem that says that every polynomial functor generated this way can be given in a container form like this. But we just collect all the shapes into one thing, and then we have one exponential. So, okay, here's one example. If I have 1 plus x times x times x, then I just collect it in a choice of left or right. And then if I'm left, then I have 0 x's. If I'm right, then I have 3 x's here. Right? But this breaks down in the quantitative setting. Because, for example, if I want to have 0 x's, then I would try to do it with 0 arrow x. But then I get the terminal type. I don't get the monoidal unit, which is the thing I can get out of. Right? And if I want to have 2 x's, then I would try to do 2 arrow x, but then I get the width, not the tensor. So I get the one where I get one of them, but not, and I get to choose, not the one where I have to have both of them. Right? So instead, we have to do it by hand for this inductively generated class. So we just formulate it directly by saying what the predicate lifting is for each inductive element. And this becomes the induction principle in the elimination principle. And it's not too hard to do this for each one of them inductively. So for example, for the tensor, we say that the predicate lifting of the tensor is the predicate lifting of the components, where we just do the projections. And again, it's okay to do the projections because we are contemplating a type here. Right? So we have unlimited use of the projections. And then the derivation of the elimination principle works basically the same as before, just that we have formulated it this way with a step function and the predicate lifting rather than for the normal form of it. Right, so it's not quite as smooth as before, but I think it's also interesting for this reason, because it's a brave new world of polynomials where for example, so this would be the initial algebra of this would be something where you have a leaf and then you have 3 subtrees, right? But if you instead start to consider putting width in some of these, then it's a tree where you have 3 subtrees, but you only have access to one of them, right? You don't get all 3 of the subtrees, but you get one of your choosing, and that's it. Which might be interesting to model something like interaction structures or trees like this, where you only should be able to go down one path, right? But okay, I think I'm running out of time. So there's plenty of things to do in the future. It would be interesting to actually construct these initial algebras for non-finite f. You could also consider linear functors rather than just linear functions, because the functors themselves are all living in the 0 fragment, so they are not restricted in any way. Right? And then you could take this internal description of what it is, and just translate it to a model and see if there's a nicer external description as a functor between the categories involved in the model. And could also hope to extend this permutation preservation that was only considered for lists to arbitrary containers, just by composing with the permutation before the container, basically. Right. But okay, that's me. Thank you.
Okay, thanks a lot. Are there questions or comments? Torsten is already up. Can you unmute, or should I do something?
Yeah, I can unmute myself.
Good.
Yeah, thank you for this, for the nice talk. I'm wondering, is there a more semantic model? I mean, since my PhD, I don't like realizability anymore. I mean, can you not do something with sets mixed with this ring R, maybe like using a writer monad? I'm not sure exactly. But,
yeah, I'm sure there's plenty of things to do. I mean, the obvious thing to do is, yeah, I think one good notion actually is if you take these models of non-linear, linear dependent type theory, where you separate the linear things and the dependent things, I think they also fit into this. I think they become these models. And then your semantic notion is something like a symmetric monadal category.
No, but hang on, something much simpler. I mean, if you think of it, these functions and the input is sort of marked with elements of the ring, and then you use it in a linear way. I mean, like the object should be sets which are somehow interwoven with these resources. I mean, isn't there anything like this, or you haven't thought about it?
Yeah, I think you're right. I think there is something like this. So I know Andreas Abel has a model like this, where it has another relational model on top of just sets, basically, and then you use the relational level to keep track of exactly this. I might be describing what you're describing. But yeah, it's a good question.
Okay, then there's a question from DG Berry, please.
Hi, so thanks for the talk. Do you get, in the wild, do you get problems with polymorphism over your row values in your ring, where you want to kind of instantiate a given definition at multiple different values, depending on?
Yes, you do. It's worked around the stupid way you would expect at the moment, where you have to duplicate your definitions. But yes, it would definitely be nice to have polymorphism in that sense. I mean, it depends a little bit on your ring. If your ring is 0, 1, many, then of course there are only 3 values, and you can always work around it by duplicating. But if your semi-ring is something more infinite, then you really need it, I think.
Thanks. And then there's a question from Steve.
I have a quick one. I think there was a paper at LIX last year by 3 authors, and I only know 2, Kishida and Selinger. The third one I don't know. And it was combining dependent types and linear logic.
Yes, it's also a nice paper. Yeah.
Okay. How is your thing related to theirs?
So theirs is quite similar, but I have this notion that types can only depend on the shape of values, and they define what the shape of something is. So they're motivated by quantum computing. So a lot of so you only really see the difference if you start to consider quantum-y things. Whereas I think for non-quantum-y things, the shape of the thing and the thing itself is often the same.
Okay.
And then it's the same as this thing. But...
Right. Thanks.
Okay, and then there's a question from Paul Taylor.
Hello. So combining linear and dependent types sounds like a type theorist way of saying this, that somebody recently asked on Math Overflow what is to locally Cartesian closed categories as to So what's the fourth thing in the locally Cartesian closed over Cartesian closed to what over symmetric monoidal closed?
Yeah.
Have you got a suggestion for that?
Not a good one. I mean, you can take, if you take this categorical semantics, which is very syntactic and basically just encoding syntax in a categorical language, right? But then, of course, there is a bioequivalence between categories with families and locally Cartesian closed categories. I mean, categories with families is some extra structure, and locally Cartesian closed categories. So you could hope to do the same thing. I mean, it's basically just rephrasing your question, I guess. I don't know the answer to it, but one answer, an unsatisfying answer, is that it's exactly this thing, right? This structure. But it's kind of cheating. And it's an interesting question.
That's a related question that a lot of people do polynomial functors in vector spaces and chain complexes and things like that. And they do a lot, and it's a big machinery, but of course that's not locally Cartesian closed either. And they never use a slice category in their life. So that's a related question. And well, what's the relationship between these theories of polynomial functors?
Yeah, it's a good question. I guess if we knew an answer to Paul's question, then we might know an answer to your question, right? Because I suspect they are instances of whatever semantic notion this is.
Okay, are there more questions? There's one from Tamo, maybe. Tamo, do you want to? Where's Tamo?
Okay, now that you unmuted me. I don't directly have a question, but I also was reacting to what was happening in the chat. So maybe there is something along the lines that Thorsten was suggesting, especially if you take the work that that Mycroft and Orchard and Petricek and company have been doing, which has to do with Coke-Lisle for co-writer type of monads, but you actually work with the semi-ring, and the additive structure also plays a role. And but it's just a comment, and I
yeah, it's a good comment. Thank you.
Okay, then I think we should thank Fredrik again and move on. Steve, are you ready?
Yeah, kind of ready. We could start trying to figure out the screen share business. Let's see here. I think it's this. Let's see if this works. How's that look?
Looks good.
Okay, do you want to wait for another minute?
Yes, I think that would be best.
Paul Taylor still has his hand up, but maybe that's not.
That's a special feature of him.
I see. Well, that's a good point. Try to get this out of the way. All right. Maybe I should do a full screen thing here. Is that better?
Looks good.
Okay.
So now it's Saturday.
Now it's Saturday for you. No.
It just changed just now.
Oh, you have 6 hours from me. Oh my goodness.
Okay, so I'm sad to announce that now comes the last talk. It's the end of the workshop fireworks. Steve Awodey will tell us about polynomial functors and natural models of type theory. Please, Steve.
Thank you, Joachim, and thanks to everyone for still being here at the very end. It's been a long week and a long day, and it's, for some of us at least, it's Friday night. So I appreciate that we're down to the hardcore here. So I guess people are interested. I'll try to make it worth your while. Oh, thanks to David too, and to the Topos Institute for organizing. All right, polynomial functors and natural models. Feel free to stop me along the way if you want some explanation. Here's an outline, and we'll see how far I get. I'm not committed to section 5, but I'm pretty committed to section 4. So I hope I get that far. I also want to point out there that the dependent type theory part comes only up front. So don't get worried. That's going to be over soon enough if you find that part painful. So here it is. Oh, fortunately, a few people have talked about type theory. I was getting a little worried there that I was going to have to do all the type theory work at the very end. But now Fred did some and Christina did some yesterday. So some of this is a little bit familiar. Okay, anyway, dependent type theory. So we have basic types and then some type forming operations here. Can you see my pointer if I drive around with it? Okay. And then there are terms. Each type can have some terms. Think of them as kind of like elements of sets. There are variables and there could be constants or other terms. And then associated with the type forming operations like this product type, there are term forming operations like the pairing for two terms, which will be a term of this type. And of course, this distinctive lambda abstraction, which is kind of the hot lick of this song, which gives you a function type. So if you've never seen a lambda before, I don't know where you've been, but I think you know what the idea is. Now, the interesting thing about dependent type theory is this idea of type dependency. So you think of a dependent type, the way to parse this expression is X is a variable over the type A, and then given that, B is a family of types indexed over A in this variable X. So you think of it as an indexed family of types. And then given such indexed families of types, there are these type forming operations, which form the sum of all the types in the family and the product of all the types in the family. That's the idea. And then there are some equations between terms, but only between terms of the same type. That's why we indicate it like this. Okay, so that's the basic setup. Now, don't be alarmed. I'm going to start drawing some turnstiles here. And the way this works is as follows. This type dependency that I mentioned, where you can have a type depending on another type, can be iterated. So I might introduce now a new variable y of this type, which is varying over this type. And I kind of moved this turnstile over here just to indicate that this is a well-formed context. A context is a sequence like that of types and typed variables depending on each other successively. So here's the kind of general setup. If gamma is any context and C is some type in that context, then I can make a new context by introducing a new variable of type C. And then given that setup for the contexts, we have the rules for those type formers that I mentioned before. So here's the sigma type, for example. Let's take it slow. Let's suppose that B is a family of types depending on A and possibly also some other junk in the context. Then I can make a new type, sigma over A of B of X. That's the sum of all the types in this family. And it still depends on whatever other junk that this thing depended on, but it no longer depends on the X. The X is now bound, so to speak, in this sigma. So that's the introduction rule for the sigma types. And then there's a rule for the terms to build terms of sigma types. If I have a term of type A and I have another term of type B of A, remember B depends on A, So I can plug that A in right there for the variable. Then I get a pair A, B of this sigma type, right? It's like, this is a weird way of explaining it, isn't it? It's like a Grothendieck construction for a functor, right? So it's a term in the base and then a term up in the fiber over this one. And then there are these elimination rules. There's a projection from, if I have a C of this dependent type, then there's a first projection. And there's also a second projection, but it has to take account of which fiber it's in. So it's in the fiber over the first projection. Okay, I probably should have said second of C of type B of second of first of C. I guess that's what it should have said. And then there are some equations here between these terms. They're just the ones you expect. The first projection, the second projection, and the pairing of the two projections. Okay, so now I did that a little bit carefully. I'm not going to do the other stuff that carefully. And in fact, I'm going to show you a systematic way of simplifying this. You see all these gammas, I only said it once, right? And then after that, I didn't have to keep saying it. And really, I don't have to keep writing it, all those gammas. So we can just introduce the implicit convention that if the gamma doesn't change throughout the rule, I can just drop it. So here are the rules again with no gammas. And then when I don't have all those gammas, then I also don't need all the turnstiles, except once in a while I need a turnstile like here to indicate that this thing is depending on that. Okay, so this is the same rules that I just showed you. It's just a little more perspicuous because it only has the relevant information without all that irrelevant redundancy, okay? But the official version, of course, is this. So now let's look at the pi types in that same style. Again, if I have a family, I can make the product of everything in the family. If I have a term depending on a variable in one of these families, well, then you can think of that as a cross-section, as it were, of the family. That is, it's a function. It takes arguments in A, but it takes its values in the respective fibers of this family. So that's the product of the family, and such a dependent function there is a kind of cross-section of the family. Okay, and then there's a application rule. If I have such a function and a possible argument, I can apply the function to the argument, and I get a term in the right element of the family. And then there are the usual equations here for the abstraction and application. Okay, so that's the products. And then there's a little bit of substitution here. Think about it this way. Let's suppose I have a type family depending on gamma, and a term of that family also depending on gamma. And now I have a substitution of contexts. This is just a tuple of terms with variables over this context and values in this one. Well, then I can plug that tuple of terms in for these variables, and I get a new setup over this context, which is just the family A with the substitution sigma and the family of elements there with a substitution sigma. So those are kind of substitutions. Usually they're given, they're admissible rules, let's put it that way. But the basic thing is you can substitute terms for variables. Okay, so that's what I wanted to tell you about the basic setup for dependent type theory. Now I want to explain a certain kind of model for dependent type theory, which I hope will make things a little bit more perspicuous. And in order to explain this model, or this kind of model, I need this concept, which is probably familiar to many of you. Let's suppose I have a small category C, and I have a natural transformation between pre-sheaves on C. I will say that such a natural transformation is representable. I don't mean it's in the image of the Oneida embedding. I mean that its fibers are in the image of the Oneida embedding in the following sense. Whenever I have a map from a representable into the codomain and I make this pullback, then the pullback is in the image of Oneida, right? So the fibers of this map over all the representables are themselves representable maps in the sense of being in the image of Yoneda. Okay, that's the notion of a representable natural transformation. And now the fact that I want to tell you about is this. A representable natural transformation is exactly the same thing as a category with families in the sense of Peter de Bière, which fortunately was mentioned in the last talk. So that's great. I'm not making this up. This is a kind of standard notion, at least among type theory people, of a model of dependent type theory is a notion of a category with families. If you know what a category with families is, I'm about to tell you why it's the same thing as a representable natural transformation. If you don't know what a category with families is, you can take this as the definition. But what I'm going to tell you now will kind of unwind the usual definition of a category with families from this notion of a representable natural transformation. It's not anything deep, but it's a, I think, delicate observation that was also made by Marcello Fiore at about the same time that I made it. I'm a little bit distracted here by the fact that I have these Hollywood squares of people on my screen. Can you see them or can you only see the slides? Okay, good. So I won't be worried about that. Oh, I have to be a little bit more precise here. So, so specifically, I want not only that the pullback, if I pick an arbitrary pullback, is representable, but I want for each such element a chosen pullback, and that one comes with a chosen span like this, making a pullback square, okay? So really what I'm saying is a representable natural transformation equipped with a choice of such pullbacks is the same thing as a category with families. So that's a kind of fine print. So first of all, the category C, the small category over which I'm making my presheaves, I think of as the category of contexts and substitutions. Remember those tuples of typed variables. And I'm going to write the objects of C in capital Greek and lowercase Greek like this, just to recall that we're thinking of these things as contexts. But really, I'm working in an arbitrary category here. I'm just building in this interpretation, okay? And now let's suppose I have such a representable map of presheaves. I'm going to write it like this. And I'm thinking then of U as the presheaf of all types. And I'm thinking of U dot as the presheaf of terms, and P as the typing relation of a term. So here we go. If I have a type in context gamma, well, then that's an element of U over gamma, because U is the presheaf of types in context gamma. And if I have a term of type A, then that's an element of U dot over gamma, because that's the presheaf of terms in context gamma. And of course, the typing relation just tells me that when I apply P to U dot, I get U. And so this is the corresponding picture, right? An element of U over gamma by Yoneda is just a map like this from the representable, and an element A of U dot is a map like this, and I compose with P and I get the type. So maybe I stop a minute and look at this, because this is really the basic idea that we're interested in. Think of this maybe, so first of all, I'm not going to write Y for Yoneda all the time. These are Greek anyway, so that tells you that this is coming from C. And now the elements of the category of types, or the presheaf of types, the universe of types, are just maps out of contexts. So I think at some point somebody was saying, oh, instead of turnstile, you just write a map into the universe from the context. Well, that's what this is. So a type depending on a context is a map into this, think of it as a universe, which depends on gamma. And a term is a map out of gamma in this universe of pointed things. right? And then this is the forgetful functor where you forget the points and you go down to the type. Okay, so that's the idea there. So we're going to go on from there. Right, I'm thinking of this as a kind of universe where this is the displayed family, and these are the indexing object of the family. Good? So now I'm going to slowly unwind the definition of a category with families, but so that I don't run out of time, I'm not going to do it that slowly. But of course, the slides will be available. So if you want to go through it more carefully, you can do that on your own time. So first of all, remember those substitutions that I mentioned, where if you have a sigma substituting, then the sigma acts on both the types and on the terms. And that's just the usual kind of pre-composition by representable acts naturally on this natural transformation here, because you're just precomposing here in the representable part. So there's your substitution of sigma into A is just A composed with sigma, and your substitution of sigma into little a is just little a composed with sigma. And if we have a further one, then of course, the category with families laws require this to hold and this to hold. This is just the functoriality of the typing. And finally, the context extension, which I think, as Fredrik said, was the kind of challenging part of the category with families, that of course is going to come from this representability condition on U. So let's see how that works quickly. If I have a type in context gamma, then I need to build a new context like this. And it has to have, for the structure of a category with families, it has to come with a substitution back to A, and then it has to come with a term of this form. So that's part of the data of a category with families. And where's it going to come from? Well, this setup here says I have A in context gamma, so that's this. And then I pull back P, and I get a representable thing here because this was a representable natural transformation. So that means this is a new Greek, capital Greek thing. That is, it's coming from the category C. And this is a map coming from the category C. So that's exactly a substitution of contexts here. So, and then the Q says, if I re-index A along P, that is, I precompose, then I have an element of that type. That's what this is saying. And that's exactly the commutativity of this square with that Q on top. So let you think that through, but that's the one of the laws of the category with families. Another law of the category with families is this stuff here, that given a sigma and given an A, you can pair them up and get a substitution. So that, of course, is just the fact that this is a pullback square, and the equations in the CWF follow from the commutativity of these triangles. And that's it. So that's all the laws for category with families. If you look at the old paper by Peter de Bière, you'll find exactly those laws, and they all follow from the concept of a representable natural transformation over an arbitrary small index category. Sometimes you put a terminal object in there just to make things easy, so you have some closed types. But that's it. Okay, so now we're going to take that and we're going to run with it. That's going to be our notion of a model of type theory or category with families. And what's so good about it? Well, the first thing I want to call your attention to is the fact that it's an essentially algebraic concept. It's kind of obviously essentially algebraic. You have to sit down for half an hour and write it down, but it's a bunch of operations, and it's I think 3 sorts and 8 operations and a dozen equations or something like that. It's a finite limit theory. So that's great. Because it's a finite limit theory, we know what the homomorphisms are. It has algebraic homomorphisms, and those correspond exactly to syntactic translations of type theories. Also, it has initial algebras. and it has free algebras over some basic ingredients. And these things correspond to type theories over some basic types and terms. And finally, it gives us a kind of new view of what is all that type theory with the rules and the horizontal lines and so on. Well, that's a procedure for generating free algebras of this form, right? Tells you how to build up the elements of the free algebra. It's just like building up the polynomial algebras. So we have a good notion of free algebras. We have finitely presented ones and so on. So there's a whole nice theory of these things regarded as essentially algebraic concepts. Of course, type theory can be seen, or rather category with families in the sense of Dubert can be seen to be essentially algebraic too. You write it down in a little bit different form and you can study the category of homomorphisms and so on. But I guess what I'm saying is here we're seeing that in a pretty immediate way. Okay, so I'm calling these things natural models because they're natural transformations, okay? So such a representable transformation, representable natural transformation, I call it a natural model. I just want to call attention to the fact that these are related to some other notions of semantics of dependent type theory that you might have seen before, namely the tribes in the sense of Joyal. Also, categories with display maps, I think, is the name of a roughly equivalent notion from the last century. There are some other names for the same kind of thing. The idea is this: suppose you have a fibration over C consisting of so-called display maps. These are some maps that are stable under pullbacks in C. Then what am I saying here? Oh, I'm going the other way. I'm saying, look at all of the maps of this form given by my natural model. So I start with my natural model. It looks like this. And now for any representable, that's an object in C, take the pullback. I have chosen one of those. That's called a display map. And those display maps are closed under pullbacks in C, right? And so what I have is a fibration of maps over C, right? In fact, it's split. And that forms a clan in the sense of Joyal. So Joyal has given a nice, clean notion of semantics for dependent types. And the connection between these natural models and the clans is this. The family of display maps forms a clan. And conversely, if I have a clan, then I can build a natural model of it. I just take the coproduct of all the maps in the clan, right? Up in the pre-sheaves, I take all the maps F and I coproduct them up. And this thing will be a natural model in this sense. In fact, it determines a splitting of the fibration. So there's a kind of back and forth here between clans and natural models. A tribe is a special kind of clan with some additional stuff. The basic notion is the clan, and that corresponds to natural models. Okay, but what we want to know now is what about modeling the type formers, like the sigma and the pi and so on. And that's where an interesting connection to polynomial functors emerges. And that's why I'm here in this workshop, because there's an interesting connection here between the type formers and the category families and the polynomial functors. So let's take our natural model here, P, and let's form the associated polynomial endofunctor. We've seen this formula several times. It's this composite of adjoints on the pre-sheaves. Here was our familiar expression of it in more, I don't know what, internal type theory of the locally Cartesian closed category C hat. This is the polynomial endofunctor. This little bracket indicates the fiber of this map over a generic element here of U. Okay, everybody know, I think I don't have to explain that any further. Here, of all places, how this endofunctor on C hat arises from this object. I'm not really going to make a lot of use now of the fact that this thing is representable. That's kind of a nice fact, and maybe I challenge you to prove that because this is representable, this endofunctor is actually co-continuous. But I think I don't really need that from here on out. So now here's a lemma though that I would have thought had been proven by now, since we've had a whole week of polynomial endofunctors. What's the universal property of this polynomial here? An arbitrary map into P of X doesn't really have to be from a gamma, it could be from anything. Corresponds naturally to the following: a map into the base, and then you make the pullback and a map like this into the argument of P. Everybody know that already? All you polynomial people know that, right? Because maybe the type theorist can just read it off, right? If I map into this, I get a pair. So the first component is something of U, and the second component is a map from that something, well, the fiber over that something back into X. So there's my pair, A comma B. So that's the universal property of this polynomial. Now I'm going to apply it to U itself. So if I apply the polynomial to the base itself, what I get, according to what I just said, was this: a map from gamma into P of U is an A, and then a B, which is another type depending on this extended context. So here I'm kind of using the fact that this is already being regarded as a category with families or a model of type theory or something like that by saying this is a type in context gamma. This is the extended context. That's the pullback. That's what we said before. And now this is a type in the extended context. So P of U classifies types in context. Good? So far, so good. And here's a little proposition now. This natural model, if you like, regarded as a category with families and therefore regarded as a model of type theory, admits product types. That's those rules that I showed you before for product types, independent type theory. Just in case there are two maps like this, I've called them suggestively pi and lambda, but they're just maps making a pullback, where what's over here is that polynomial functor P that I told you about right there. That functor P applied to this map. I take my P, my, if you like, arbitrary map, right? I make a polynomial functor, and then I apply the polynomial functor to P itself. That's this guy. And then I have a pullback square like this. That's exactly what it takes to interpret those rules for pi types when I regard this thing as a model of type theory in the sense of a category with families. I think this is just amazing. So I'm going to try to kind of walk you through it, although I realize that it's a little bit much if you're just seeing it for the first time because you're not used to thinking about this. But let's go through it, and then I'll do the other cases a little more quickly, but you can always look at the slides later. So this thing, remember, is this polynomial endofunctor applied to the base, U. So that classifies types in context. That's what we said a minute ago, right? And now this constructor takes a type in context. I'm calling it a constructor, but really it's just a map. It takes a type in context to a type, right? So that's what it does. It takes this thing and it returns this thing. So I've interpreted here that rule that said, if above the line you have this, then below the line you have this, and that for an arbitrary gamma mapping into it. Okay, so that's what this map does. It interprets this type constructor. Upstairs here, this said, so what is this? That's my polynomial functor applied to u dot. So those are the elements or the terms. So if I have a term of this type in context A, then this map returns a term. And what type does the term have? Well, apply P. And it turns out it has this type, namely going around the other side. What happens if I go around the other side? Well, I forget the B, because that's what this functor does to you, to the map going from u dot to u. It forgets the little b, and it returns this, and then it applies the constructor. So the commutativity of this square is telling me that if I apply lambda to this term in context, its type is pi of this type in context. Okay, so those are the introduction rules for the type theory. If I wanted to make you dizzy, I would flip back and forth between the slides now and recall what the rule looked like for these types, but maybe you can do that yourself. You know, it had this above the line and then this below the line and this above the line, this below the line. And those rules are exactly modeled by saying the polynomial functor applied to this gets a commutative square. Why is it a pullback, the commutative square? Well, let's have a look. Let's suppose I have a type family like this, and then I make the pi here, and then I have a term, an arbitrary term of this type. Well, if I have any term of pi type, remember there's an associated application here that I can make with the property that when I apply lambda to it, I get the f back out. And in fact, that this is a unique assignment, f of x given the f, is shown by an easy diagram chase here that this is a pullback. So the two equations that I showed you before tell me that this thing is a pullback. So that's my kind of sketchy sketch of this proposition that says, apply the polynomial functor of p to p. If you have a pair of maps here, making a pullback square, then you've modeled the rules for pi. Okay, so far so good. Let's try the sigma and see what happens. So the proposition is, this thing models the sums, the rules for sigma types, just in case, again, there's a pair of maps making a pullback square. But now what I have here on the left is something different. It's not just the functor p applied to this little p, it's some other gadget. Down here in the base, it's the same. But up in the domain, this q is something that looks like this. And if you're a polynomial person, you'll recognize this as the polynomial representing the polynomial endofunctor, which is p squared. So I make the endofunctor capital P associated to this thing, and then I compose it with itself. And now it's a fact that the composition of two polynomials is a polynomial again. And so this thing is a polynomial. It's represented by a map, Q, and that's this map right there. So I put that map right there, the composite of two polynomials. And now I make a pullback square. That's exactly the rules, all four of them, the type former, the introduction, the elimination, and the computation equations for sigma types, is to say that this is a pullback square. There's the type former, there's the introduction, and the pullback squares elimination. Okay, I'm not going to do it again with the red and the blue and everything, but you can work it out yourself or you can read the paper. It's pretty straightforward. Let's do one more simple example. Here's a really easy type, the terminal type. Fred already mentioned it. It's a type in any context here, any gamma. It has a term, and any term is equal to that distinguished term. So that's it. So here's another one of these pullback squares. This terminal type is modeled by this category with families. Just in case there exist these two maps like this, this is the terminal presheaf, right? That's the identity, of course, and I have a pullback square. So that's exactly a model of these typing rules, okay? So let's stare at these two pullback squares for a minute. Here's the one that I just showed you. Here's the one that I showed you before that. Remember, this is P and this is P squared, regarded as polynomials. And these are pullback squares. Now, if this was a real seminar, like in a seminar room, at this point, I would wake you up by saying, what is this? Who knows what it is? And then the sharpest people in the room would shout out that they know what this is. So who's going to raise their hand and say what it is? Oh, Torsten, you already know. Anybody else who doesn't know? No. Does anyone who doesn't know? No.
I don't know.
You don't know? Come on. This is a polynomial. This is P squared, and here's a Cartesian square. This is a polynomial. This is the terminal polynomial. It represents the identity. And this is a Cartesian square.
So it's the unary operations.
This is a nullary operation, and this is a binary operation. Those are Cartesian natural transformations between the corresponding polynomial endofunctors. So this represents an endofunctor P. This represents P composed with P. This Cartesian square represents a Cartesian natural transformation from P squared to P. Everybody good with that? We had a tutorial. Richard went through this pretty carefully. This is a room full of experts on polynomial functors. So I hope you guys are happy with this. Maybe I'm wrong. This one is the identity endofunctor. This is the P endofunctor. This is a Cartesian natural transformation from the identity into P. That's exactly this thing. Good? Can I get a hands up if you're happy, a thumbs down if you're not? This is the part where I'm suffering from not actually being in a room full of people. I don't want to go on until you get this, because this is the punchline, really, of the talk. The rest of it is just gravy. Everybody happy with this? Okay, Joachim says thumbs up. That's all I needed. So here's the proposition now. If I have a natural model regarded as a type theory, it models the terminal type and the sigma just in case the associated polynomial endofunctor has the structure maps for a Cartesian monad, right? Cartesian natural transformations of this form. This is Clive Newstead. A lot of this stuff, the best place to learn it, if you want to look it up later, is not my paper, but Clive's thesis. So Clive worked out a lot of this and a lot more in his thesis, and that's always the best place to learn something, is somebody's thesis. So that's what I recommend you do, is read Clive's thesis. So let's, this actually, I want to spend a minute on this. This is the structure for I've said it kind of in a sneaky way. It's the structure maps of a Cartesian monad. I'm not saying it's a Cartesian monad because this is just the structure. We haven't checked the equations yet, right? So what would the equations, the monad laws, mean if we regard this as a type theory and we regard these as rules of inference in the type theory? The monad laws are equations between these operations. In the type theory, the monad laws correspond to something that makes sense, namely these familiar or more or less familiar type isomorphisms. Look at that. These are kind of known type isomorphisms. I'm not saying we should add these laws. These things already hold in any category with families that has sigma types and a terminal type. We're kind of getting this structure for free somehow, but there's a problem. And I'd be happy to have some advice on this problem. The problem is this: these equations don't hold as equations, right, for that structure. However, these isomorphisms do hold in type theory if you kind of spell out those types. So what this suggests is there's a higher dimension of structure that we need to consider, and we need to replace these equations with some isomorphisms, and then which correspond to these type isomorphisms. And then what we'll have is not a monad, but a pseudo-monad, right? Up to that higher dimension of structure. So it looks like there's some kind of a higher dimension of structure in the bi-category of polynomials, which we'd like to make use of in order to capture these type isomorphisms. That's something that Clive and I pursued. There's a suggestion in his thesis, which may or may not be the last word on this subject, maybe not, but at least it was an idea and we pursued it and it worked, but there's probably more to be said. So have a look, if you're interested in this topic, have a look at that. I think that's a good avenue to go. Now I'm running low on time, so I'm going to hurry up a little bit. What about the pi type? Remember, we looked at the pi type before. That was this pullback square. Now that we've started thinking of this in terms of polynomial endofunctors, we see that what this thing is an algebra. It's saying that P is an algebra for this polynomial endofunctor P. Well, I have to lift it first to the arrow category, which I can do. So I lift P as the endofunctor up to the arrow category, and then this is saying that this generating map is itself an algebra for the P lifted to the arrow category. And now you'll ask me, oh, what about the algebra laws for a monad, algebra for a monad? Okay, so here's the, I guess it's a theorem now rather than a proposition. It was a proposition before. Anyway, it models the pi types if I have an algebra structure map like this. And the algebra laws, of course, also correspond to some interesting type isomorphisms, namely these. So those are some familiar laws in type theory, some type isomorphisms. And again, it doesn't hold on the nose, but it holds up to a putative higher dimension that remains to be exposed. Okay, so that's what I wanted to say about the polynomial monad. I guess this should be in scare quotes here, or it should be a pseudo-monad or something like that. If I had more time, I would spell out the solution that's in Clive's thesis, and then we could say polynomial pseudo-monad here. But what I'd like to do instead, I have a couple of minutes remaining, is show you a little something here about propositions as types. So I said before that a representable natural transformation can be regarded as a category with families. Let's suppose I have in the presheaves a universe in the sense of Hofmann-Streicher, or maybe a Grothendieck universe, or an object classifier in a infinity topos, or something like that. We don't have to be too specific. It's not necessarily a representable map with respect to C. However, it is, of course, trivially representable with respect to E hat, right? And so I can still regard it as a natural model. The contexts now are just all the presheaves. And this thing is representable because it's a map in the presheaves. So I can do that same kind of modeling that I was doing a minute ago with respect to a universe like this. So now I want to consider the following idea. Let's take this universe and let's take the image factorization. This image factorization, of course, is stable under pullback. And so if I have any context and any type in that context, then when I pull this image factorization back, I get the image factorization of that type. And that is exactly the propositional truncation of this type family. If you know some homotopy type theory, otherwise think of it as the support of the family of types, right? So it's either of those things. It's the propositional truncation, or it's the support of that family of types, or the bracket type in terms of dependent type theory. So this gadget here, this image of the universe, is a universal family of small propositions. So that's a very simple construction. Now we're in a topos here, and this is a mono, so we can classify it by a pullback square. And this mono is in particular a family, and so we can classify it again with respect to U, as long as we've taken our universe to be big enough that it contains all the sieves. So I get another pullback square like this with a classifying property. And now I want to consider what happens if I compose these two maps. So I claim that if I compose these two maps, well, first of all, I get an endo map on the universe, which I'll call absolute value or norm or whatever, propositional truncation. And this thing is exactly the modality on the universe of propositional truncation. This is a way of constructing that modality. And in fact, if you compose them the other way around, it's not hard to see that what you get is the identity using the uniqueness property of the subobject classifier. And therefore, this modality here is an idempotent, and its splitting is the subobject classifier in the topos. So that's kind of cool. We get this subobject classifier as the image in the universe of this modality of propositional truncation. And now what I'd like to do is use that to compare these constructors that I just showed you that you may not have seen before, the sigma and the pi acting on this polynomial endofunctor. Remember, here was the polynomial endofunctor. It looked like this, and I applied it to the universe, and I got my pi constructor and my sigma constructor. And now, if I restrict down to the subobject classifier along this P of this I, where the I was this, I is inclusion, S is support. So here's the I, and then I take the support again. What I get is the familiar topos theoretic quantifier. Everybody knows how the quantifiers look in topos theory, right? I mean, you're not used to seeing this sigma here because you do it for one type A at a time, or one object at a time, but you can do it for all the objects at once, and then you don't have to put a subscript A on here. So there's the existential quantifier in your topos. It takes a family of sub-objects on A and it returns a proposition. And if you apply the I, and then you apply the sigma, and then you take the truncation, what this shows you is this sigma type is really kind of proof relevant version of the existential quantifier, or the propositions as types version of this. And similarly for the pi. The Topos theoretic universal quantifier is just the type theoretic pi type restricted down to the propositions which are contained in the universe. So I hope that makes these operations a little bit more scrutable, comprehensible, by recognizing that they're just the good old Topos theoretic operations that you already know and love, extended to the universe. And they behave in the same way, just like these things behave by homming in and then letting them act. That's how you get them to act on the sub-objects. You hom in and then you act and then you take the sub-object. Here you do it on the type families and it acts in the same way. Okay, that's it. Here are some references. That's kind of maybe the first paper. Here's a paper with Clive. Here's Clive's thesis. So that's the main reference. And then the propositions as types stuff and also some of this other stuff is in this work in progress with Nicola and Sina. So have a look at that if you want to see more details on that. Okay, thanks. We finally made it to the end of the week. It was a long, hard slog. Thanks for staying with me. That's it.
Thanks, Steve. I see there are already some questions. Let me guess who's the first two. Let me guess. It's Torsten.
I have a question.
Good guess.
So, oh yeah, no, Andre first. I mean, that's fine.
Well, thank you. My question is, well, that's very nice. It's very beautiful. My question is, what happened to the distributivity law that we love between sum and product in this setting where you have an interpretations of sum and also of pi?
Yeah.
What do you do with the distributivity law, or is there something to say?
I think that it's of the same kind as these other laws that I showed you, that we get it for free from the rules of type theory. That's well known to the type theorists. What does it mean in terms of the polynomials? Well, I guess Richard showed us what it means in terms of polynomials. Why does it hold in terms of this polynomial monad structure? I don't know. I don't know. So, I mean, it's there. We don't have to add it. It follows from the rules of type theory.
Because abstractly, of course, monads are very common in in the theory of operads and polynomial monads. So for sigma, what it is saying is that you just have a monad. Wow. But then for pi, something a bit curious is happening, surprising,
I agree.
which I don't really know how to interpret in terms of the theory of monads or operads. So that's puzzling.
Yeah, I agree. It's a puzzle. And also these, algebra laws here, we seem to get them for free from the rules of type theory. At least we get them up to isomorphism, but
yeah,
they popped out. Why? I don't know. Also, it's the same, it's the same question really as these monad laws, right? I didn't say, suppose we have a polynomial monad. I said, suppose we have these structure maps for a polynomial monad, and the equations don't hold, but these isomorphisms do hold. They follow from the type theory already. So implicitly, there's a kind of higher dimension of structure here where the monad laws hold, just given the monad structure. So something funny is going on there that I don't understand.
Is it not because U is a terminal family?
Yes, I think that's why. I think that is why, but that's a very sophisticated answer, isn't it? So
But if it's the terminal, it cannot fail. So
yeah, I think that's kind of it. But I mean, terminal in what sense? It's terminal as a classifier for small families or something like that, right?
okay, let's move on the list. Torsten.
Yeah. This is this is really very beautiful, and there was a discussion just in the chat, but I think you get the axiom of choice just from the sigma law, so it should be a consequence. The type theoretic axiom of choice should also hold. I mean, does hold in your models, and I think it's very, very beautiful because when categories with families were introduced, people say it's very ad hoc and very syntactical. But you showed that this is not the case. It's very simple. You take a polynomial monad, and then you have an algebra with a monad, and whoops, you got the type theory with pi and sigma. That's really, really nice. Yeah.
It's amazing. Yeah.
Yeah. And as you know, I mean, I knew the sort of the sigma story. I mean the sigma universe story. But here I have a puzzle for you. Conor McBride showed that is a generalization of monads, which are quite useful in functional programming. These are called applicative functors, and they're basically lax monoidal functors over the product. And every applicative functor is a monad, but not every monad is an applicative functor. No, the other way around. Sorry, the other way around. Every monad is an applicative functor, but not every applicative functor is a monad. So what happens? I know the answer, but it's a puzzle. What happens if you replace monad by applicative functor?
I don't know.
Yes. You get products, non-dependent products.
Okay.
So I don't know whether you can. I don't know whether you can have calculate the non-dependent functions also in a similar way. I mean, maybe there's the algebras of an applicative functor. I don't know exactly what this means.
Maybe, yeah. Oh, I see the chat now. Oh, there was a long discussion in the chat. I'm glad I didn't see it while I was speaking. That would have distracted me. Okay, I'll read this discussion later. I'll try to save the chat and see if there are any questions later.
Okay, and now it's Paul.
Really, just a compliment. I mean, I had this definition of universe in my thesis, which introduced display maps a very, very long time ago. Now these things.
Sorry, Paul. Which definition did you have in your thesis exactly?
Well, your U dot over U was in my thesis.
When you used that notation?
I didn't use that notation. No, I don't know what notation
I don't know what the definition is. You mean a representable natural transformation?
No, it wasn't.
Okay.
It wasn't.
If you just mean a map as a universe, that's a Hofmann-Streicher maybe universe. The key here was the representability.
Yes. Okay, I didn't have that. I'm just making you a brief compliment, actually, Steve.
Sorry, I interrupted.
Okay, so this universe is not by any means unique. There could be another one which is maybe you describe it as homotopically equivalent to it, but not the same. Now I realize that the quantifiers and the like would be endos functions of that structure, and I thought they would just be a mess. But it's amazing to see, how neat it is that you.
In fact,
you did that. So I'm wondering how your monads vary according to replacing the universe with a homotopically equivalent one.
Well, the thing is, there are even more than you have in mind. Horatio. Anytime you have a tribe in the sense of Joel, you get one of these. And so there are many, many different universes for all the different tribe structures on the small category C. And it's just a family of maps, right, that are stable under pullback. And every different such family will give rise to a different universe. So there are tons of different such universes.
Right, okay. Now, I didn't know the words tribe or clan. Can you say briefly what they mean?
Yeah, there's a display map categories.
Right, okay.
In your sense.
In my sense, right. Okay.
That's one that definitely did have first there was the display map category, or category with display maps or something like that. But for any such one, you get a universe, right? You just take all the maps, all the display maps, and sum them all up, take the co-product of all of them up in the pre-sheaves, and that's a universe.
Okay. Okay, thank you.
Yeah.
Okay, Nicola.
Just a couple of comments. Maybe this thing about equalities versus isomorphisms.
Yeah.
And maybe it's just one of those situations where the pullbacks of U can have many automorphisms, but the maps into U, they're just a set. And therefore you don't have the space to track these automorphisms.
Right. I think that's right. And so it suggests maybe doing this in another setting, in groupoids or in infinity topos or in hot.
Yeah.
And then those isomorphisms will have enough room to become.
And a question, for many of us, the interest in polynomial functors came from this paper of Ike, Mordek, and Eric Palmgren, which I don't know if it has been mentioned already, in which they treated W types. Have you considered looking at W types in your setting? It's a kind of way of closing the circle.
Yeah, yeah. I've thought about it a little bit, where I think that if you have such a natural model map, representable map, it might not have sigma types, but if you take the W type of the polynomial of that thing, I think that's the freely adding sigma types. It's kind of like taking the symmetric monoidal completion.
The free monad on it.
Yeah, it's like the free monad on it. I think that adds the sigma types. I think that Marcello and I talked about this at some point because we were kind of looking at species. He might have worked that out, but I think that's the case.
But you also might want to consider what it means for you to be closed under W types.
Yeah.
Yeah. Okay. Thanks.
Can I ask a question?
Yes, please.
Can you go back one slide?
Oops. Is that it?
No, it's the one where you have the pi, this one, yes. So let me try verbally to draw some pictures.
Yes,
so let's say U is the set of all corollas.
Ooh.
And U dot is the set of all corollas with a marked input leaf. Then if you take P of U, that's the set of all two-level trees that you decorate corollas with other corollas. So P of U is two-level trees. And then did you say this is a pullback, right?
Yeah, so now I think I go back to the pi type. Where is that?
Well, I was precisely, I could not understand the difference between the pi type and the sigma type, just what the left map is concerned. Could it not be the same map?
No, the pi type has the polynomial functor P applied to this map. The sigma type has P squared. over on the left. So this object is different. It's not P of U dot, it's this thing.
But you said that it's the composition of P with itself.
Yeah, it represents P composed with itself.
Because, I mean, if you agree that to draw the elements in U as corollas, then if you take P composed with itself, you should get a endofunctor whose operations are two-level trees.
Yes.
So P of U is two-level trees.
That's it.
Yeah. And then you pull back that point.
So this is a kind of composition of the two-level trees into a single one, yeah?
Yes.
And then I pull back the marking here, the point.
So that gives you a two-level tree with a marked leaf.
Sounds good.
Okay, but why didn't you get that for the pi type too? Because if you go back to the pi type, then P of U dot should be to decorate a corolla with pointed corollas. Ah, you get many points. Okay, see if this sounds correct. P of U dot is a set of two-level trees with a marked leaf in each of the upper level trees.
That sounds right, Jan.
Okay, okay.
Good.
So I don't know. I mean, there is also a pi operation in somehow. Another monad, another multiplication on P. I mean, there is sigma and pi. Because, no, am I wrong? Maybe I am wrong.
On the endofunctor P, big P.
Yeah, well, I understand the square.
Yeah. And then here's the other square.
Mm-hmm. Okay, I have to think about it.
Okay. Maybe one way of thinking about it is this. If we think of this, if I had a piece of chalk here, I could explain this better. Let's suppose we have, I'm going to draw it right here, okay? Let's suppose we have a gamma here and we hom into U from gamma. Then we make a pullback, that gives us a map over gamma. Instead, if we hom into this thing, then we get not only a map over gamma, but a second map over gamma, right? Because it was a map in context. And now there are two things that we can do. We can compose, or we can take a pi along the first map. And that's what these two different operations are doing. You're taking the sigma as the composition and the pi as the pi. So if we kind of hom into this, get the corresponding structure over here, and do the operations, then Yoneda will give us this map. I don't know if that's helpful.
Yeah, it seems
without chalk, it's hard.
I don't know. Maybe I don't know if I can just add one comment. There is some kind of dissymmetry between pi and sigma, right?
Yeah.
And this analysis that you're providing is showing up this dissymmetry. They don't. Although one is left adjoint and the other is right adjoint to substitution, they definitely have different role.
Yeah.
And somehow, yeah. I'm saying that, but I don't really know what I mean.
Well, maybe if I can just take a moment, I'll mention one of the ideas that we had for exposing this higher dimension of structure, and that was regard this map as, am I still there, or did I get messed up? Yep. Take this map and make the full internal subcategory generated by the map. I think maybe everybody knows how to do that, right? I think as a family of objects, and I build an internal category.
Yeah.
Then I can show that that internal category, for example, is Cartesian closed if we have these structures of sigma and pi.
Okay.
Whenever I have a pullback of such maps, that's a full and faithful functor of the corresponding internal categories. And so these structure maps are giving us internal functors on corresponding internal categories. This is the category of internal types. This is like a slice category of that. And these maps are the internal adjoints of a corresponding kind of pullback functor here.
Okay.
So that's a useful way of thinking of this if you like that sort of thing. You make the associated internal categories associated to these polynomials, and then the Cartesian squares become full and faithful internal functors.
Okay.
And you can analyze these operations in terms of internal functors. That's just one possible analysis.
Okay. Yeah. Okay. Good.
Yeah. That's all I got, folks.
Are there any more questions? Well,
as the last speaker, I'll take the liberty to thank the organizers.
And we should extend this thanks to Tim Hosgood, who has been doing a lot of hard work to make everything work with the Zoom sessions and the YouTube and the videos. Well, everything behind the scene is basically Tim. So we should thank Tim also. And thanks everybody for coming and staying up so late. And well, David, anything else we should say?
We are thinking about having a second incarnation of this, but we'll be in touch about that. And yeah, thanks to all the speakers. This was great. And thanks for everyone for coming and participating. So we'll be in touch with maybe some sort of survey or something afterwards. But yeah, thanks again, everyone. Good to see you. Next time, maybe in person. We'll see.
Bye.
Okay, bye, everyone.
Goodbye.
Bye-bye.
Good night.
Yes, good night.
Thanks, Steve. That was fantastic.
Yeah, thanks, Steve.
Yeah.
Yeah. See, how do I save the chat?
I would just highlight it and copy to a clipboard or something.
Okay.